Good morning. Hope you guys are good. I'd like to apologize firstly for not being able to post this video yesterday. Unfortunately, I was on duty on Friday throughout the night until the morning, and I had a class with my students that I teach physically. Now, unfortunately, I never got to rest, you see, because I only could rest after 3 a.m. Okay, so I've just taken a nap rather than, a proper sleep. Anyway, guys, enough of the excuses. I just wanted to apologize so that you don't wonder why I didn't post this early enough. It was because of those issues. And I mean, it takes a lot of work, guys, and concentration to get these papers done fully. But I'll try to do this easy paper, the prelim paper, to just be on some revision streak, so to speak, so that you guys can at least get ready. This is not to say these are the questions to come, but it's just strategies you can employ in each different type of question as you go along in your paper. And then, of course, we hope that all your preparations have been adequate. Okay, obviously there's lots of videos in the channel that you could easily have used to do proper revision, because I always try to make them as comprehensive as possible for this purpose, that you don't need too many to look at what you probably need. Anyway, multiple choice question 1, there's instructions essentially boil down to saying choose only one answer. You can't choose more than one. Ideally or intentionally, it was meant to be a situation where there's only one answer to each question. But now it has happened that sometimes we see more than one answer. Now we wonder, was there a problem? Usually it suggests there is a problem with the question, or the typist put a wrong symbol, or even the person who designed the question was confused. Yeah, we have to think about it, because why would it happen? There has to be some understanding of what is going on. Now, here's the question. Which one of the following homologous series? Now, what do we know about homologous series? This is a group of organic compounds that can be described by a single general formula, or at least by the same general formula. Now, it contains the hydroxyl group. Now again, we've got another issue. What is the hydroxyl group? When we see a hydroxyl group in organic compounds, what does it tell us? Obviously, this is one way of the examiner telling us that this is the functional group. Okay? It is the functional group. Again, another concept for definitions. What is a functional group? This can be a bond or an atom or a group of atoms that is responsible for the chemical properties of a group of organic compounds, because this functional group belongs to a particular group of organic compounds, all right, or set of organic compounds. So this is very important. These are things, as you go along, you try and analyze and use in your head to also, get a bit of revision. This is when you are revising. Obviously, in the exam, you just need to understand the significance. You don't need to write it down. Okay, the question again asks, which one of the following homologous series contains a hydroxyl group that is bonded to a saturated carbon atom? Now, what is the significance of that? Saturated carbon atom. What does it mean? But in any case, the functional group, we know that once we see that functional group, we're talking about alcohols. And we see ketones, no. Aldehydes, no. Yes, no. So the answer here is A. Sorry, C. It's alcohols. But now you may not be so sure, because the question said saturated carbon atom, because all we know is that it's a saturated carbon atom chain rather than carbon atom. But anyway, this is just to suggest that the carbon atom occupying the hydroxyl group is itself fully occupied, not to have any more extra bonds, but it has only those bonds that it already has plus the hydroxyl group. And we know that according to this knowledge of functional groups, that is a signature of alcohols. All right, we move on. Consider the compound shown below. Again, here, key is to find the longest chain. So 1, 2, 3, no. 1, 2, 3, 4, 5, yes. So we always find the longest chain. Now, what is next? We then prioritize a particular functional group. Now we know the carbonyl group at the end of the chain or at the beginning of the chain says we've got aldehydes. So this is an aldehyde. Okay. So aldehydes have a suffix al. Al. Okay. Or nal. N-A-L. All right. So now let's see what is going on. So now that we know that the parent chain is a pent, 1, 2, 3, 4, 5, so it's a pentanal. Now we look at the position of the side branch, which is the methyl group there. Obviously, how do we number the carbons? We prioritize the carbon bearing the functional group. Then that should be number 2, number 3, number 4, number 5. So that automatically gives us that position of our side branch. Again, even if this was not to be priority, we must have the least number of carbons leading up to the position of a side branch, not the most. Okay. Now, the question says the IUPAC name of the above compound is, so this is 2-methyl pentanal, and that's the one. That's the one. Can you see? When you know these things, you just go for it. But what would be these others? Obviously, this is the commonly made mistake by students. You start coming from the other end instead of prioritizing things. Remember, this is priority. Again, this helps you to become better even in life, to prioritize what is important over all the other things. You need to work less than to work more as you grow older, because your energy levels actually drop. Your ability to be resilient and to take more actually decreases over time. So this is why you need to be able to understand things enough to use your experience to work a little bit less than any ordinary individual who doesn't have any idea of how to do things in a smart way. Yeah. Right. So we're not going to make this any longer. We continue. Consider the reaction. Now, what do we see here? We see this structure right here. This is propene. We don't know where this is. Okay, maybe it's prop 1 in, because that's all we can have. So this is an alkene. Why? Because the general formula is CnH2n. As we can see, we've got 3, and when we double that for the hydrogens, we get H6. Now, alkenes are capable of a certain type of reactions, additional reactions. Okay? Addition reactions. Now, that's very important. And now we look at what we just reacted it with. It's a chlorine chlorine gas, sorry. Now, chlorine gas in its diatomic format is what we call a halogen. All elements of group 7 in that diatomic format, we call them halogens. But if that was to be an atom, an ion like that, we call it a halide ion. That's why we talk of halogens and halides. The halides are the ionic forms of those elements of group 7, and the halogens are the diatomic format of those elements of group 7. Now we can clearly see we are doing an addition reaction, because everything gets swallowed up into this molecule. So this is nothing but a haloalkane. Haloalkane. Okay, all right, okay. Now, it says the name of the reaction. Can you see the question is saying name of the reaction? Now, the question is it this a general name or is it a specific name? Because you need to be able to separate the two. There's a general name. there is a specific name. Sometimes, okay, not always. Now, the general name would be, we are adding an element of group 7, so it becomes halogenation. Do we see something like that? Yes, there it is. Now, that's it, because we can see this is hydrolysis, reaction with water, hydrogenation, reaction with hydrogen gas, hydration, reaction with water, or addition with water. So at the end of the day, this becomes the correct one. So this means we're stuck with the general name. What would be the specific name? The specific name would be chlorination, because we are adding a chlorine. So if we added bromine, we call it bromination. Of course, this is very important, and this becomes what we would call the type of reaction. This is the general type. So please, guys, be very careful. General type. Be particular about these terms, type versus name. Of the names, general versus specific. It can be very useful in the longish questions. Of course, in the MCQs, it doesn't really matter much, but it is very, very, very important to make sure this is very clear in the head. All right, we move on. Consider the vapor pressure against temperature. So vapor pressure and temperature curves for 3 chain isomers. Now, again, chain isomers, it means these ones must belong to the same homologous series, isn't it? Because for them to be chain isomers, it means first they must be described by the same general formula. Then we can change the shape or the length of the molecule. Usually when we say chain, that means we are varying the parent chain by branching it out. Okay, great. Now this is under standard atmospheric pressure. Okay, that is very important as well. So what is standard atmospheric pressure? This is the pressure of 100 kilopascals, or that is it 101 101,3 or something pascals. I think it's something like that. Yeah, I forgot that constant, but anyway, that standard pressure constant is actually one that signifies, I don't know why this thing does screenshots. It is the one that signifies 1 atmospheric pressure. Now we can see we've got a topic, so for every graph there will always be a topic. So also when given an opportunity to do a graph, please show us the topic. All right, now also label the axis. This is very important. The axis must be labeled as well, so that we know what is in there. All right, now we can see that, well, we've got some temperature here, T1, at which all these molecules, when looked at according to T1, we see that the vapor pressure is 101 for compound A, but the pressures for B is less than that, and the pressure for C is less than that. So that means at a given temperature, the one with the highest vapor pressure must be the shorter chain. Because we're saying chain isomer, so that means we're varying the chain length. So that must be a shorter chain compound, okay? And then B must be of intermediate size, and this one is going to be long. This is intermediate, between the two, intermediate. So this one you cannot define it clearly except between two others. Okay, now the question says again, or at least we can see that, well, what is this one? This is 1 atmospheric pressure, so meaning it is equal to the atmospheric pressure. And now we can clearly see that when we say the temperature at which the vapor pressure of a given substance is equal to the atmospheric pressure, this is called the boiling point. So that's the boiling point of A, and that's the boiling point of B. And that should be the boiling point of C. Can you see? This table is giving us more information when we look at it properly. And sometimes this is what actually is the essence of the question, but they don't make it so obvious. These are higher grade questions, guys, where the concept being tested or asked is slightly behind what is given, but what is given can lead into that conclusion. Now, here's the question. It says, now consider the statements regarding the curves for the 3-chain isomers. Okay, compound A has the shortest chain length. Yes, that is possible because we saw that with the shorter chain length, it means the strength is lower in the IMFs. Okay, the intermolecular forces compared to the others would be less. Why? Because the shorter chain provides a lesser surface area for the action of these intermolecular forces, whereas a longer chain provides the greatest surface area, and that means it becomes bigger. Now, if I can just expand your knowledge a little bit, if we think of an atom, just a single atom in a molecule, okay, so we would have the nucleus there at the center, which is positive, and then we've got electrons orbiting in their orbitals. Okay, now these electrons, of course, the ones closest to the nucleus don't move at high velocities as the ones in the outer energy levels. Why? Because these ones, the electrostatic force between the nucleus and those electrons is much stronger. And Coulomb's law helps us to understand why that electrostatic force would be stronger than this one that is far away from the nucleus. So the longer the distance, the smaller is the force of attraction. Now this means these ones can move at relatively higher velocities than these ones. Now this creates a scenario where we will find that in this very same atom, with the nucleus over there positively charged, we end up with this electron having moved to this side, however slow it does, and the other one has caught up with it in one position of the atom. Because these are in constant motions, we call them spins. All right, now let's have a look. What happens when this is the case? Now, when most of the electrons are on the one side, they make this position or this side of the molecule slightly negative. Okay, sometimes we use these, the deltas. That would be negative, né? And this side, it becomes positive because this other end, when all of this happens, this other end becomes slightly positive. Now, if we bring in another ion, another atom or another molecule, we bring in another molecule. Now, I'm using Niels Bohr model to try and get you guys to understand this. But some of you who've been watching my videos, the grade 11 and grade 10 videos where I was explaining the significance of the radius or diameter of an atom or the distribution in the periodic table, this came out nicely. So I'm sure you would have understood it. So we would have an electron here and an electron there. They are catching up. So what are they creating? They are creating this situation right here where we see that this end of the molecule is negative. Maybe let's put our positive there. That end of the molecule is negative, okay? Now the negative will attract the positive. Now depending on how many electrons are participating, can you see there's 2 electrons here? Maybe I should space them up a bit so that you can appreciate what is going on. Okay, but let's do it anyway. We will say this electron will be attracted to the nucleus that way and that electron to the nucleus. Can you see? We end up with 2 bonds of the same order, so to speak. Of course, varying degrees of strength and what, but at the end we assume these are all the same, okay? So these are what we call instantaneous dipoles within a molecule. And this is what we then call the induced dipole induced forces. Now, what do we call these ones? London forces. Okay, these are London forces. So this is how they occur. This is when a molecule is partially dipole because of the movement of these electrons and their different velocities due to their commitments to the nucleus and of course the distance to the nucleus. And then these ones start attracting each other because this is happening frequently. Hence these molecules are going to be bound together somewhat by these dipole-induced forces. So this is essentially the essence of this. And then of course with other atoms, when we've got hydrogen bonding, between two atoms bonding, we would see that the bond is sort of like moved more to the other one because of its electronegativity, which again is related to its radius. The smaller the diameter of that atom is, the closer are all its electrons to the nucleus. That means they are tightly bound, and hence that one cannot give up easily. It rather wants more electrons. And the other one, which is less electronegative, is happy to give electrons away to achieve a bit of stability in its outer energy structure. So this is, all about the octet rule if you think about it. Okay, all right, okay. So now we understand what we understand, and now we want to put it to use. So can you see, guys, now my analogy, the reason why I brought this up was to say, if you've got a single thread like that and then you hold it at the ends and you pull it apart, it can snap easily, right? But if you take the same cords, maybe you align them like that and there's 3 of them, and then you find a way of holding them at the end, right? Try pulling apart. To snap this would be more difficult. Now this is to suggest that the bigger the chain length, the more electrons participate in this, and therefore those intermolecular forces of an equal strength are not so easy to separate when acting together. But when it's a single one at a go, you can actually separate them that easily. Isn't it true that we are stronger together than as individuals? It is so. So this is why chain length, when we increase it, it means we're increasing the molecular mass and we're increasing the number of electrons that participate in these forces. And the more of them, the stronger those bonds become, even though individually the bonds are of a weak strength, but when combined, they actually become stronger. So that's the idea. It doesn't mean that the type of intermolecular forces changes per se, but it's because now there are many at a go. Now it's not so easy to separate many people than you would separate 2 people. Okay, I hope that is clear. Now it says the boiling point of compound B is at T2. Is that true? Yes, we can see that at T2, the vapor pressure of compound B is equal to 1 atmospheric pressure. And that is the definition of a boiling point. But it's not coming so directly. But remember, that is it. Okay. Compound C is at a gaseous phase at T2. Let's have a look. This is just before, T2 is just before the boiling point of C. Now that should be a liquid because we can only boil a liquid. Okay. At least that's what we know. Can boil. All right. Liquids boil. Now we see that, okay, that is not exactly true. Can you see, once you understood the issue of boiling point here, it became easier to determine the phase. Otherwise, you could easily be fooled here and not be so sure what is going on and end up not knowing what to select. But now we know for sure A is our friend because we understood our table much better than actually it was given. Now, like I said, folks, be very careful. The type of questions you get in the MCQs are the same questions you are going to get in the longer questions, but more detailed. Sometimes they can even help to understand a question you may have skipped in the MCQs. Sometimes knowing how to answer that question in the MCQs can actually assist you in ensuring that you score your marks even in the longer questions. So sometimes this can help each other out. So when you skip a question, don't flinch. You're still going to come across similar concepts, but maybe they can be brought in a way that can help you remember the rest of what you probably couldn't remember for this particular question you are skipping right now. The fact that you've made an effort and understood where you got stuck, this is why You need to attempt every question as you go through it, but if it takes time, skip it, knowing that you've tried it, because as you get more clues in the paper, because there will always be clues ahead for a question you couldn't answer before. Or sometimes if you could answer it before, or perhaps you could figure it out eventually before, it means it could be a clue on a question that's still coming. So always be on the lookout. Sometimes if you look back at some of the questions that are similar, you can actually get some clues rather than to keep thinking you're going to just think on the outside. Sometimes think within the paper, because the paper has all that you need. Anyway, let's go on. Now, it says consider the synthesis reaction of ammonia. Now, this is the Haber process, isn't it? It's a reversible reaction in a closed system, but of course, none of that was mentioned right now. Now, the rate at which N2 is consumed, meaning the use up, during the reaction is X mole per decimeter cubed per second. All right. Now, which one of the following is the rate at which ammonia gas is produced? Now, remember, the molar ratio becomes important when two substances are to be looked at. Yes, overall, on average, that's why we say average. On average, the rate is the same for each, but technically, for a specific component or participant, because of its different commitments in the participation, or should we say different roles. As you know, in a group, there are certain individuals who work more than the others within a group. But at the end of the day, overall, the group is looked at as good. But sometimes there's just a few key players in a team that actually make the team shine. The others are supporters rather than, the key things or the key factor. So at the end of the day, when we isolate these, we will know that the amount at which they deliver some work here is going to be proportional to their positions in this setup. As we can see, this one is an invisible one. You never write 1, okay? It's considered as, whatever it is. And then we look at what is happening. Ammonia is 2, so 1 is to 2. That means every single mole of nitrogen gas that is used, 2 moles of ammonia gas are added or are produced. So this would mean that essentially using the molar ratio, if the molar ratio, let's just say molar ratio of substances is going to be 1:2, it means now the actual rate will also be divided into that. If this is X, therefore this one must be 2X. We double that, and that's B. So when we understand these things, guys, it makes life so easy. You don't have to sweat through this question. As much as it is tough, but it's not that tough for you to spend a lot of time in it, provided you know what to do. Okay, now consider the following reaction at equilibrium. Okay, we've got cobalt tetrachloride ions in solution plus water, and then we get cobalt crystals. So once this is the water of crystallization. When you see that within a chemical formula, you know that is crystallized. Okay, right. And we have also the chloride ions. Nice. Now we are told that this dude is blue and that dude is pink. Okay, so this means cobalt tetrachloride ions in solution are blue and then cobalt crystallized or cobalt crystals are pink in color. Okay, nice. Now what is the question asking? Remember, we're told this reaction is at equilibrium. Okay, that means Le Chatelier's principle will apply. Now we are told the solution is currently pink. This is suggesting that the forward reaction is being favored. Okay. Now, concentrated hydrochloric acid is added to the equilibrium mixture. Concentrated. Now that means it has a higher concentration of its respective ions. Now hydrogen or HCl is a strong acid. that dissociates completely to form a high concentration of hydrogen ions, as well as a high concentration of chloride ions. Now when we add this here, what are we going to do? We will notice that the chloride ions are common between this equilibrium mixture and this solution of HCl. Now as a result, this is going to increase the concentration of the chloride ions in that system, and that would constitute the disturbance, as would be stated. Disturbance, is it disturbance? Now that would be the disturbance. And now if we disturb this, Le Chatelier's principle says we will favor the reaction that cancels that effect. That means the reverse reaction. Remember, initially we favored the forward reaction, but now we're going to favor the reverse reaction because we want to decrease this to almost normality. Of course, it's not going to be exactly normal, but it will have to decrease rather than to have a sharp effect. And of course, this is the concept called common ion effect. This is quite a popular thing in chemical equilibrium, so please know the common ion effect basically says our equilibrium mixture has an ion, the chloride ion, whereas the solution of the HCl has the chloride ion, and this Cl minus ion is the common ion basically. Okay, nice. So this means we will be favoring the reverse reaction. Nice. Now it says here, which one of the following combinations correctly describes the effect that the addition of concentrated hydrochloric acid will have on the equilibrium constant? Now the equilibrium constant, Kc, has not anything to do with a change in concentration. So there will be no effect because this one only changes with temperature, okay, not anything else. So there will be no effect, and anything otherwise is wrong. So this is already suggesting C and D are eliminated from the possibilities. Now we look at the color change. The solution turns pinker. No. Remember, if we're using up the cobalt crystals here, that means we're going to lose their concentration essentially, and that means the pink color will disappear, it will fade, and the blue color will start to pick up. So it should turn more blue, not pinker. Okay, so the best answer is B, because it ticks all the boxes. Okay, irrespective of what happens elsewhere. Now, which one of the following substances can be classified as Laurie-Bronsted acid? Now it's a proton donor, isn't it? So can Na2 donate a proton? No, this is a weak base. Now KOH, it's a strong base. This one you may not be so sure. NaCl is just a neutral salt. I'll just say NS. The neutral salt. So this one should be the guy. Sometimes when you're not sure, the process of elimination becomes your absolution, okay? Because an absolute elimination will occur so that you only have one question. The one that you're doubting and you don't know what to do about it is most likely the answer. But in the longer questions, one can say, show that the resulting pH is acidic. Now, you would have to take our NH4 plus ion and react it with water, right? And then what do we get? This one would protolyze the water by donating a hydrogen plus. Now it forms the oxonium ion plus ammonia. Can you see? This is what it's suggesting. And now this represents a strong acid, meaning a strong acid initially reacted with a weak base, because this is a strong acid, this is a weak base. Now when we reacted a strong acid and a weak base, we produced an acidic salt. This is part of the salt, because we produce salt and water. This was part and parcel of a salt. Now this salt was acidic because we could see that we reacted a strong acid and a base to produce it. Now which ones? Usually this would be HCl, but not always. Be careful. This would have been ammonia and HCl, and then would form ammonium chloride salt. Okay, so this is the idea behind all of these things, because remember, these reactions can be looked at in reverse. They are usually reversible actually, but we focus on one direction at a go. So this is the idea, guys. This is the idea. All right. Okay. All right. Now, I'm sure you understand now what is going on, because if one has to justify the production of the oxonium ion, or you guys call it the hydronium ion, it's still correct, is basically the proof that the resulting pH is acidic. And this is on the question of hydrolysis of salts sometimes, or just pure acid-base reactions, meaning strong versus a weak. Because I mean, this is a salt and this is water. Water can also be looked at as a weak base, so to speak. All right, because it's an ampholyte. Now consider the salt CH3COONA. This is sodium ethanoate. Now, what is this kind of a salt? This is a basic salt. How do we know? It's because we reacted ethanoic acid CH3COOH plus a strong base sodium hydroxide. And that's how we ended up with this CH3COONA and water. Is it water? It must be, because this one will protolyze that thing. We must produce water. No? Now, if we look at this, what happens here? We can clearly see if we eliminate the spectator ion, what happens? Water will actually protolyze that thing, or at least hydrolyze that thing back to a weak acid, but and a strong base. But now the strong base will only show up with the hydroxide. Can you see? It's just a reverse reaction technically. Now, which one of the following combinations correctly identifies the hydrolysis reaction? Now, this is reaction with water. Where do we see it? It's on the left-hand side. Now, it should go that way. Of course, we may eliminate the spectator ion, because this one is a spectator. It doesn't change its, this is 1 plus, this is 1 plus on this side. So this is a spectator. Sometimes it may be included in an explanation reaction or may not be included. And also the pH. Obviously, we said this is a basic salt. How come? Because we know when we hydrolyze this salt, we would end up with a strong base by the production of hydroxide ions. So this is good, because we can see there's our friend, and the pH is definitely going to be greater than 7. So that should be the answer. Of course, this is true, but the pH is not less than 7. This is absolute nonsense. This is absolute nonsense. All right. So I hope, guys, as we move along, you can appreciate the level at which your knowledge should be at. Obviously, it don't always have to be like this, because not all of us can be the same, but be around the fence somewhere, be near, that area of framework, so to speak, so that you don't fall off the mark when things are hotting up. Okay, consider the cell notation of a galvanic cell. Now, a galvanic cell, what do we know? This is cell potential of this one is positive. If it is positive, it means these are spontaneous reactions. No, they don't need an external source of energy. All right, and with the notation, we know that this double line represents the salt bridge. And we also understand that this portion represents the anode. And then that portion here represents the cathode. Always, we start with the anode, salt bridge, cathode. And of course, the order in which this occurs is so that we're starting in the right direction. This is aluminium solid into aluminium ions. So this is oxidation. So at the anode, oxidation takes place. At the cathode, reduction takes place. Okay, very important. And reduction will start here again and move in that direction, meaning we're taking the permanganate ion and reducing it to the manganese 2 plus ions. But because these are ions, they are not a solid, so they are in solution, then we need an electrode for that, and we use platinum. But why platinum? Because it is chemically inert. Okay, it's chemically inert, and 2, it is a conductor of electricity, because we need something that can conduct electricity, right? And at the same time, if we're using molten forms of our solutions where there's a bit of temperature, it has a high melting point. Okay, sometimes you may find graphite chosen as well. So that is the influence of choosing those. They are chemically inert, they are good conductors of electricity, because this is what we're doing. We have to conduct electricity through the electrode, and of course these have high melting points, meaning if ever we are using molten solutions, meaning hot solutions, then these would not, dissolve or something and end up interfering with our experiments or what the purpose of that reaction is. So graphite, which is carbon, can also be used in the same way. Now the question says, okay, which one of the following reactions occurs at the cathode? So at the cathode, we know that reduction takes place. Now reduction in a chemical equation, we will see a substance, whatever it is, I'll just say subst plus electrons going into some substance, whether in ionic form or solid form or whatever, but there are no electrons. Now once you see electrons to the right of the equation, this would be reduction. Okay, now when we see a substance going all the way into some other substance plus electrons, it means these electrons are released. Once you see these electrons on the right, this would be oxidation. But be very careful, examiners have a tendency to write things the same way, and then you have to dance with who is stronger than who. The stronger oxidizing agent will take a precedence over the weaker. At the same time, a stronger reducing agent will take precedence over a weaker reducing agent. So be able to use the table of standard electrode potentials when these are not written in a way that you can see, especially when this is written like that and this is written like this as well. Now it will depend on their strengths of oxidizing ability for us to choose the correct one. Now let's have a look. Manganese 2 plus ions to the permanganate ion, can you see? And we are releasing electrons. This setup is already wrongly written. The notation, or at least the format, is already suggesting oxidation, and that's not the case, because we saw that that would be the cathode, because it's after the salt bridge in the notation. Now the permanganate ion, it's acidified, and then we add 5 electrons. We reduce this to manganese 2 plus ions and some water. This is correct, because we see that electrons are added on the left, and in fact the direction is also good. It's from left to right, not right to left, which is this one. Now aluminium solid to aluminium 3 plus ions plus 3 electrons, this is nothing but oxidation. So it has nothing to do with reduction. This is read from right to left in our table of standard electrode potentials. Now aluminium 3 plus ions plus 3 electrons on the left, this is definitely reduction, but is it the reaction taking place at our cathode? No. What is taking place at our cathode is that one. So this is definitely reduction, but it's not the correct one for this particular galvanic cell. Again, we know that aluminium 3 plus ions are weaker oxidizing agents compared to the permanganate ion. It is the strongest, one of the strongest oxidizing agents. So essentially, between the two, that would be, okay, maybe I didn't shade the right one. Now we end up in trouble. And now, between these two, the oxidizing agent, or what substance is undergoing reduction here, is the stronger oxidizing agent. So can you see this further emphasizes our choice for B? Of course, do consult the table of reduction potentials or standard electrode potentials, because this helps to make the decision when these reactions are written together and you have to choose the correct one. Even if we didn't see the cell notation, we would know if aluminium and this permanganate ion are involved in a galvanic cell, and we have to decide which one is the cathode, which one is the anode. Without the help of this notation, we would then use our standard reduction potentials and rate which one is the strongest, which one is the weakest, because the strongest is the one that's going to take part in that particular reaction, and the weakest is actually a stronger reducing agent on the other end. Therefore, it would undergo oxidation rather. Okay. Now, a spoon is plated with silver during the process of electrolysis, and we saw that electrolysis, essentially, we can use it for electroplating, we can use it for purification, for cleaning, and also in the chloralkali industry, we can use it to produce sodium hydroxide, chlorine gas, and hydrogen gas, which are very important in industry. Like we know that the chlorine gas, we can use it to produce detergents which help us to clean things, and it has a wide range of redox reaction that it takes part in, so we can use it for different purposes. Sodium hydroxide, it's a very strong base, we can use it in many reactions as well. In organic reactions, you see most sodium hydroxide is a strong base that if you dilute it can actually create alcohols and what, and those are useful for different purposes in industry and in our daily lives. Hydrogen gas is also very important. Make margarine, for example, what you guys call butter. Sometimes I don't understand how things are called in this world. Anyway, whatever. Margarine, we need to do a hydrogenation there. And that's how we solidify that thing to a nice and, something you can spread on your bread and stuff. So all of these things are not just a joke. They are there for a particular reason that we need to respect and recognize. Anyway, now the difference between a galvanic cell and an electrolytic cell, we know that here we have an external source of energy, whereas those ones are spontaneous reactions. Now with an electrolytic cell, we know that the E cell is negative, right? Meaning these are non-spontaneous. Reactions. Okay, we need an external source of energy. Then of course the longer bar, like in all electricities, is the positive terminal, and the shorter bar would represent the negative terminal, and that means this electrode here becomes negatively charged. The one connected to the positive end becomes positively charged. Okay, so what does this mean? It means we are stripping electrons off this one and driving them to this side. That's why this one has an excess of electrons. This one has a deficit of electrons because of this battery here. Now what happens when we strip those electrons? We actually force silver ions to form into the solution. Now, when these ones go and join into the solution, but this one being negatively charged, we then attract them in here to pick up those electrons, and that's how we end up with a silver coat here, because then silver forms on top of this. Then over time, of course, if we let this go on and on and on, this one will become heavier, this one will corrode. Now what happens here? Unfortunately, with the galvanic cell, we know that the positive terminal is the cathode. Cathode is positive and anode is negative. But now here, anode is the positive one. That's the difference. And cathode is the negative one. So cathode becomes the negative terminal, whereas the cathode is the positive terminal. But still oxidation takes place at the anode, still reduction takes place at the cathode. Easy. Now that's it. We have tried to have a look at it, and now we can answer the question. Which one of the following graphs best represents the concentration of the silver ions in the electrolyte? Best, not necessarily the correct, the concentration of the silver ions. Can you see for every silver ion that we pick up to make silver on the spoon, a silver coat on that spoon, there is a silver ion that is released into the solution. So we actually replace it. So if we replace it, that means we're creating an independent situation. If we were to think probability, having balls in the bag, you pick one and you replace. So it does not affect the probability of picking the others. So this should be B, because it means the concentration would be constant. Why? Because as we pick up a silver ion, we are releasing a silver ion into the solution. Otherwise, these others are just there to confuse you, because why would it drop when we replace it? Why would it increase when we are taking it? Why would it increase and then slow down? What could be the reason? Yes, in different scenarios, this could be an issue, but be careful to answer the question appropriately, focusing on the question at hand and the scenario at hand. Okay, so I hope, guys, this is clear and it's nice. So let me make myself a cup of tea, and then we move along to question 2. Now, organic chemistry, guys, forms the biggest section in chemistry paper 2. So you need to capitalize on this. This is fairly easy to handle. Then we start the inorganic chemistry here, where we are dealing with, reaction rates and stuff. And we are dealing with all these others. But remember, reaction rates don't necessarily represent inorganic chemistry. This could also be a part of the organic chemistry. For example, we could be producing methane gas, and we want to use that as, whatever we are trying to do. So this is applications of certain, sections of chemistry, rather than you would call it a specific topic. You would see that this can be, reversible reactions in chemical equilibria. This could be acids and base, or maybe acid-base reactions. This could be redox reactions, many other things. But usually, because we're doing this in the school lab, we tend to use redox reactions or acid-base reactions. Why? Because these are exothermic reactions, and they are fairly spontaneous, meaning they don't need an external source of energy. If we combine the substances, the reaction takes place automatically. And then we can tweak temperature nicely and other things, because we don't need the industry to do these things. And therefore, we can predict what direction those reactions are going to take, depending on what we have changed. So we are going to really enjoy this ride. Let me just make that cup quickly. All right, let's go on. Now, this is the beginning of some trouble. This is the beginning of some action here. Now, we know that the first question here is fairly easy. Now, consider the organic compounds A to E below, okay? This is 3-methylbutanone. So, that one tells us that we're dealing with a ketone. Just classify it sometimes, don't spend too much time. And then we've got B, CH37 plus Cl. This would have been an alkane, CnH2n plus 2. But now we replaced this one with a chlorine. So this is a haloalkane. Okay, now this is an alkane. Okay, now we look at this. The triple bond tells us we have an alkyne and it's branched, so we don't really care here. We'll just write what it is so that at least we know where we are. Now this, once we see this situation right here, this is a carboxylic acid. Okay, great. Now, we don't want to waste time. It says define functional group. Can you see? Didn't we see it? The hydroxyl group in the very first question of the MCQs. Now, our analysis, if we just go back to remind ourselves, can you see? Functional group. And having revised that a bit in our heads, here it becomes a free mark because this was indirectly, indicated in the MCQs. Usually, most of the indirectly indicated situations or scenarios in the MCQs, the ones that are hiding behind answering the question, are going to be, again, examined in the long questions. So be on the lookout for these similarities. If it was the case 20 years ago or 25 years ago, and it still is, therefore it means the chances of this being the scenario are very high. Okay, what is a functional group? We say that it is a bond, atom, or a group of atoms that are responsible for the chemical, mainly chemical, but also part of it physical, responsible for the chemical and physical. Don't write like me, write properly. Let me write properly as well. And physical properties of a group. Remember, this is a particular group, of a group of organic compounds or organic molecules. Because remember, a functional group belongs to a particular group. Those that belong to carboxylic acids, we call them carboxyl groups. Those that belong to alcohols, we call them hydroxyl groups. So essentially, you need to not have another question being asked when you're giving a definition. So this is very good. You have your easy 2 marks. Can you see? We've already thought about it in the MCQs, and now it's coming back. Can you see it becomes nice? Write down the letter of a compound that. So we've got 2.2.1 that contains the carboxyl group. Carboxyl group is carboxylic acids. E. 2.2.2 has the general formula CH2NO. Now we know that this can either be a ketone or an aldehyde. Okay, now what do we have here? We've got the ketone, so that should be A. Now 2.2.3, it says now has an empirical formula of, so the key with this one, in case you didn't see it, it's the general formula of alkenes plus the oxygen that makes up these guys, because there's a double bond with the carbon and the oxygen, isn't it? Yes, so that's the idea, just in case you didn't notice that. Now, which one has the empirical formula CH2? Okay, now we need to look at the molecular formulae. The skill in answering this question, we need to look at the molecular formulae and see. Now, this one has 3. It's going to be carbon, hydrogen, and oxygen. Can you see this one only has carbon and hydrogen? So it means it has to be purely a hydrocarbon. So anything that is not a hydrocarbon is out. So we can't look at A, we can't look at B, we can't look at E. But this is between C and D because these are hydrocarbons. Now can you see, once we narrow down where we need to look, we are good. Now what do we do there? We look at the molecular formula. This is 1, 2. So this is C2H. How many? 1, 2, 3, 4, 5, 6. So H6. Can you see? This is nothing but alkanes, right? Right. Now if we're doing an empirical formula here, we always take the smaller thingies and we divide by it. So what we end up with, CH3. Okay, so now this one is saying CH2. It means there's a mistake here because it is the one. It is the one. It is the one because we can see that's the one. Why is this one not the one? So we've got 1, 2, 3, 4, 5, 6, 7. So we've got C7H. 1, 2, 3 plus 3, that's 6, 7, 9, plus 3, that's 12. So C7H12. Now, can you see, if we divide by 7, 12 cannot divide 7 into something like that. So it's already not the one. So that means it's meant to be C, but the examiner or the typist wrote it wrong. So sometimes there's errors with these provincial papers, but we can appreciate that that should be C. At least that's what we can choose. Don't leave the answer blank, because when the marks are given, you get the marks. But if you didn't answer this, you left it blank, even when the marks are to be given because of the mistake, remember, what does the instruction say? Answer all questions. Where is it? Answer all questions. If you do not, when there's that mistake or error and the marks are given, then you become the one who's left out in the cold. So be very careful. Instructions are key. So 2.3. Now, 2.3 says, how will the molecular mass of compound E compare to ethyl methanoate? Now remember, we know that carboxylic acids are isomers of esters, isn't it? And that means if they have the same molecular formula, they will definitely have the same molecular mass, isn't it? So it should be equal to. But let's prove, are they isomers in the first place? So now methyl methanoate is going to be 1. This one. Sorry, ethyl, it's C like this. 1, 2, 3, 4, 5. Then that's that. Methanoate, ethyl methanoate, this is that. So we've got these hydrogens. Now this is C3H356, right? Now what is this molecular formula? 1, 2, 3, so it's C3H, this is 356. So can you see? Same molecular formula, different structural formulae. So these are definitely isomers. They are called functional isomers. But now, if they have the same molecular formula, they will have the same molecular mass. So it is equal to. So we write that. Okay? Now, we are told to give a reason for the answer. We can say these ones have the same molecular mass. Of course, the question that was not asked, we can call them functional isomers. Okay, maybe you may have to slot it in, but usually you get a mark for saying equal to, and then maybe 2 marks for the explanation. The idea that says they have the same molecular formula, Yeah, if they have the same molecular formula, in fact not mass, because we're comparing their masses, they have the same molecular formula. Okay, be careful of what you write. And you see, I was already making a silly mistake, because now you understand, you become careless. Be very, 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 very particular when you know the answer to the question, because it can easily go out the window. And you wonder, why, Lord, why am I making this mistake? Because you took it too easy. When it's easy, that's when you become more obsessed. Now write down, okay, we're going to have 2.4.1, the structural formula of compound A, okay? Now we can see the parent chain is bute. There's 4 carbons, and then a methyl group on the 3rd carbon. So let's start with the parent chain. So this is 1, 2, 3, 4. Now remember, butanone, it means this can be on the 2nd carbon, okay, the oxygen. Even if we place it here, it would still function as the 2nd carbon. Hence, they don't even waste time by writing butane 2O. They wrote butanone because no matter where we place this, it will not change its name. If it is a ketone, it has to be on the 2nd carbon. This is a symmetrical molecule, so it allows for that flexibility. But now we prioritize our functional group, meaning this should be carbon 1, 2, 3, 4, because the functional group must take priority. Okay, that would be that carbonyl group. Now what do? We just add the hydrogens. And then of course on the third carbon, because we said 3-methyl, we can put a methyl group. Maybe let's put it on top. Then of course hydrogens. So that would be it. Of course, I'm just explaining now with all of these other things. You don't write these other things, you just write the structure nicely, and that's all. Now we're getting 2 marks. So the position of the functional group is important, and the position of the side branch is important, because this was already volunteered that this is a butane 2-one of some sort. So we knew that it's going to be 4-carbon chain, the longest chain. Now we are sorted, guys. So we walk away with our 2 marks. 2.4.2. Now what is this saying? It's saying we need the IUPAC name of compound E. Now there's 3 carbons. This is prop. Now this is a carboxylic acid, so it's propanoic acid. Nice. So this one is just 1 mark. No, 2 marks, okay. Now we've got 2.4.3. Says the IUPAC name of compound D. Now there we go. Can you see, knowing what we are dealing with is very nice. Now we just need the longest chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So the longest chain is this one. Can you see how this molecule in question, in the MCQ question, it was bent? Now we're still getting a similar thing. Can you see it's coming back, folks? Be in the lookout of these things. Now we need to prioritize our bond. Now the list, okay, the carbon that carries the smallest position or the lowest position is the one by which we describe our double bond. Now we cannot come from this end because there's too many carbons to this carbon. But from this end, there's just 1 carbon to this one. So this must be carbon 1, carbon 2, carbon 3. And we always classify the bond to be in the position of the lower carbon of the 2 that participate in the double bond or triple bond or whatever. So that would be carbon 2, 3, 4, 5, 6. So we can see that we've got a methyl group on carbon 4. We always start with side branches, right? So this is going to be 4 methyl. Now we saw this is hex 1, 2, 1, 2, 3, 4, 5, 6. So this is going to be hex. Now the position is 2-ine. Okay, that's the one. That's the one. So how do we get the mark? Of course, we get the position of the substituent or side branch, the parent chain, and the position of the double bond or the functional group. So that gives us 3 marks. So be very good at these things. They are not so difficult. Here you really take marks usually. Okay, I call your question in the palile pana. Okay, good. So we've got here 2.5. 2.5 says B is a secondary haloalkane. Now it says draw the structural formula of compound B. Okay, not a problem. So secondary, it means the secondary carbon carries the haloalkane. Now what is this? This is 3 carbons, and then we know that the secondary carbon should carry the chloride atom or ion. Okay, that's the one. Now this is a secondary carbon because it is bonded to 2 other carbons. That's how we define this. So as a result, it becomes that which is being said. Now we're just getting 2 marks, the position of our, functional group, so to speak, and the rest of the chain. Nice and easy. Now, using molecular formulae, write down the balanced equation for the complete. Once you hear that word complete combustion, what do we get? We get carbon dioxide plus water. If that was to be said incomplete, what would you say? Now it means we're going to produce carbon monoxide plus water. Okay, this is usually what happens in cars, and hence they're fitted with what is called the catalytic converter, which converts that carbon monoxide to carbon dioxide, which is a bit less toxic for the environment. But carbon monoxide is more toxic because it can bind into the hemoglobin molecule irreversibly. That means the hemoglobin molecule is not going to carry oxygen. Although the saturations are going to be so good on the monitors, but you're actually not oxygenating at all. And that's how you die, okay? And plants cannot use carbon monoxide also. They need carbon dioxide to produce food. So it's very important to not emit carbon monoxide into the environment because we get an incomplete combustion in the engines. Great stuff. All right. Okay. All right. So now we can do this one nicely. 2.6. We know that we saw that compound D is C7, H12 plus oxygen. We're burning it in air, right? Then we're going to form carbon dioxide plus water vapor. Okay. Now, what happens here? We need to balance. So we start with the carbons. There are 7, there's 1, so we need to put 7 there. Hydrogens, there are 12, there's 2 here, we can put 6 in there. And then the oxygens, how many are they? Now there's 2 this side here, there's 7 by 2, that's 14 plus 6, that's 20. So we can just put 10 in there, and that's it. It's done. How many marks are we scoring here? 3 marks. So for the left-hand side, right-hand side, and the rest of the stuff, we carry our 3 marks with a big smile. So guys, this can be very nice, but be very careful. Calculations can be added here. As you can see, this question was a low-key problem, so please be able to calculate the empirical formula. And interacting with molecular formula. Calculations, I'll just say that. Because this is the biggest question here that can carry a lot of marks and can be technical. It is very important to know that as much of these questions are very easy, there is a lot of room for some serious trouble. Okay, good. Now, let's move on to question 3 quickly. Now, what are we saying here? We're saying the relationship between boiling points. Can you see? We saw it indirectly implicated and essentially very important in answering that question in the MCQs. Now it's back. Can you see what I mean, guys? This time I cannot really change by much in an instant. Okay, now the relationship between boiling point and the number of carbons. Can you see? We're still talking about the chain length. Number of carbon in a straight chain primary alcohols are investigated. Now the following curve is obtained. All right, we see that essentially the trend, this time we can't talk of direct proportionality because this is not a straight line. But we can appreciate that this is more like a logarithmic function, but hey, let's leave that for now. But we can safely say the trend is that the increase in the number of carbons leads to an increase in the boiling point. And why? Because we said the more the merrier for those forces to take place. Remember, primary alcohols have only one hydroxyl group each on the primary carbon. So there's only one side for the hydrogen bonding. But now what is responsible for this trend is not the hydrogen bonding, but it's actually the London forces, because they become more and more and more and more as the chain length becomes longer or as the carbons are added into the chain. So this is very important and very nice. As you can see, it's very easy to follow. Okay, now let's go on. Define boiling point. Didn't we speak about it in the MCQs? Now it's coming back. It's coming back directly. So 3.1 with 3.1.1. So boiling point is the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure. Easy. Can you see, guys? Easy 2 marks. Again, you have been primed in the MCQs for this. So it should already be there in the back of your mind that, hey, I must be on the lookout for this one because it's coming to haunt me. So 3.1.2 says, what is the structural similarity between the alcohols that makes this a fair investigation? Okay, now remember, these carry the same functional group. So that is what is similar to them, right? Because the rest is different, the chain length is different, but it's good in that we have kept the functional group constant. That is the controlled variable here. So can you see some questions you just have a way of answering them if you understand the concept behind. So what is the thing here? It's because they have the same functional group. So now we can compare them in terms of chain length. So we can just simply say they have the same functional group. Okay, or you can say only one OH minus group in each, to suggest that we don't want to have too many hydrogen bondings taking place because it can affect our investigation of assessing the chain length. So obviously, guys, this is when you're just trying to make sure you're not losing anything, because if you're saying everything, you're just emphasizing that in case I didn't place it nicely so that someone who's marking me understands what I'm saying, I'm also giving some additional information for them to actually get the picture in case, because remember, sometimes you're not so good with words. That's why we put things in brackets to just elaborate a bit more, just to make sure no one misunderstands us. But the idea is that this is literally what is being kept constant. Okay, saying the same functional group, it means that is the controlled variable, and essentially the only thing that's changing with these ones is nothing but the chain length, and that is very good. Okay, easy 1 mark. But you can't just say something careless there. Make sure if you feel like I'll clean it up, you try and explain what is going on, because that is what makes them similar, the OH minus group. So 3.1.3. Now what do we say? Which van der Waals force is responsible for the trend observed? Can you see? We knew that it's not the hydrogen bond, but it's the London force. Okay, great. Because van der Waals forces are 3. It's hydrogen bonds, dipole. You can call them ion dipole, but those are just dipole forces. And then we also have the London forces, which is the induced dipole-induced forces. So the one that is responsible for this trend, because it's the chain length which is hydrophobic in nature, it's the London force, as we explained in the MCQs. Can you see, guys, all of those things we spoke about? Now it looked as if we're being crazy, wasting time trying to explore those, but we're actually making our lives a whole lot easier when we get to these questions, because now we are cruising. We are truly cruising. We are on cruise control. Write down the IUPAC name of the alcohol with a boiling point of approximately 410 kelvins. Now we need to understand the smaller scale. That is 100. That should be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Yes. So the smaller thing is the tick is actually 10. So there's the 410 there. Okay, use a proper pencil and we can see that is 410. So that would mean it will have 5 carbons. It will have 5 carbons. So do indicate this with a broken line on the graph. Okay, if it is provided, of course. So now this one has 5 carbons, and remember this is a primary alcohol, meaning the hydroxyl group is on carbon number 1. So we can say this is pentane 1-ol. Okay, it's pentane 1-ol. So we're getting 2 marks for the position of our thingies and the parent chain. Nice and easy. So 3.2. It says another investigation is carried out to determine the effect of structural differences on the boiling point. Now the table below shows the different compounds on their respective molar mass under, sorry, that was used in this investigation. Okay, so we've got butanone, that's a ketone. Then we've got butane 1-ol, that's an alcohol, but you can see that we've got a bit of changes in the structures. Can you see what are we changing here? The molecular length per se, or the chain length, is pretty much the same if we think about it. The carbon chain, when we talk about chain length, we're talking about the carbon chain, not substituents. Okay, now we've got almost the same chain, and what do we see though? We changed the functional group. And look at the molecular masses. They are slightly different, but they're not too different, comparable if you think about it. Now look at propanoic acid. Of course, it's 3 carbons. It's shorter than these, but it's comparable to them again, all right? Because it has 1 more oxygen in it. And we can see here that the molecular mass is equal to that one of butane 1-ol. Nice. So now this is trying to spice it up. Again, this is a carboxylic acid because of the oic ending. So these are at least relatively comparable in terms of chain length, but we can safely say the only difference between these is the functional group. So this is what we are changing literally, because the molecular masses are also comparable. Yes, that one is smaller, but not enough to say we can read a lot in terms of that alone. Okay, great. Now it says which compound A, B, or C will have the highest boiling point. Now the highest boiling point is going to have the strongest intermolecular forces between its molecules. So it's definitely going to be CY. In carboxylic acids, there's 2 sites for hydrogen bondings, which are the strongest intermolecular forces we know. On top of that, the hydrophobic ends is comparable to the others. So there won't be so much of a difference for us to say a lot already. So that would be the one. So 3.2.1, that should be compound C. Now 3.2.2 says, fully explain the answer in question. So we always have this question, guys. And this one needs to be done properly. Now remember, we chose C. Now we need to speak about why is C above O. Now we need to compare these 3 nicely, because we have to actually make a proper comparison to all 3 rather than just choosing one. Because for 5 marks, we need to say something about each. Now, we can say C has 2 sites for hydrogen, for strong, let's say it, strong hydrogen bondings between its molecules. In addition to weak London forces. Sometimes I don't know, man. London forces compared to B, for example, which has compound B has only one side of hydrogen bonding in addition to weak London forces. Okay. Nice and easy. Now I'm trying to think, what do we say about I'm trying to see now. We need to say something about A. Okay. We said C has two sides for strong hydrogen bondings. Has two sides for hydrogen bondings between its molecules. In addition, in addition to weak London forces compared to B, which has only one side of hydrogen bonding, in addition to London forces. With C, we can say with A having, we can say weaker. Sometimes when something is weak, in between weak and strong, we say it's weaker. Having, as A has, maybe let's just say, whereas A has a weaker okay, maybe when you say weaker, maybe it would be better to say weaker and then this one is weak. Maybe weaker, because we say weak, weaker, weakest, so it gets worse and worse. So we can say with A, whereas A has weak dipole forces in addition to weaker London forces. Okay, good. So I do believe, folks, I do believe we have done some justice for that first bullet. Some bullets can be intense. Now we can go and talk about the energy requirement. We can then say more energy is required to separate molecules of C than the other two. Okay, we don't need to say more. Hence, C will have a higher boiling point. Nice. So of course this one can take a minute to construct, but make sure what you say, guys, makes sense. It's very important. So technically, this is very key. Two sides for strong hydrogen bondings. Very important. This one has only one side. Very important. And then of course, the dipole force is very important. So can you see the 3 marks? We need to mention the strengths because these are comparable in terms of chain length, so to speak, even in terms of molecular mass. So we can appreciate that the only change is essentially the functional group. And then of course the energy requirement is the other mark, and the conclusion. So this is how we score these 5 marks. So always look at the marks and think of the right way, or at least an appreciable measure of explanation that can capture those 5 marks, because you can't get 5 marks for saying just one thing, maybe commenting about just one molecule only. You see, each one of them is a little bit special. It's not the same functional group. So we can't just bind them under one general statement to describe them. We need to be a bit more specific because the question said fully explain. That means we need to be a little bit more in depth in our approach. Of course, guys, if we did not commit any mistakes anywhere, this could be our lovely 12 marks. Okay, I hope that is proper. Now, folks, we need to not waste time. Let's cut to the chase. We need to finish this organic section nicely and in style because we've got the ability to do so. So I hope you guys can see exactly the planning. You can see the clues within the paper to certain other questions within the very same paper. So I'm sure when you get stuck, try to look around the question paper as I have highlighted to you. You guess what? You might just find all that you need. Now, let's just enjoy this organic, because I mean, guys, these are free marks. Believe me, here it's possible to carry as many marks as one needs. So it's very important to make sure those marks are picked up and snatched if necessary. Now, we are told to consider the 3 organic reactions, 1, 2, 3. Now, reaction 1 is pent-1-ene. It's an alkene, unsaturated. We're adding hydrogen chloride or HCl. And we're forming a single compound P, which is the major product. Now, we know that this type of a reaction is an addition reaction. Right? And when we're doing addition reactions, we use Markovnikov's rule. Just say MKR. Okay, that's what we need. That means the richer get the richest, the poor get a little bit. It's always the case, isn't it, in society? Yeah. Even when we lose, the rich will lose less and the poor will always lose more. So the poor Shem are the Aram scap cells of our country, or any other nation for that matter. Because when there's a chance to lose, they lose more. When there's a chance for gain, they gain less, unfortunately. Now, that's it. We are happy with that. So we're going to form a haloalkane, basically. Now, organic compound P, same one there, the haloalkane, we are reacting with a base. Ooh. It gives us the vibes of hydrolysis, but no one tells us whether it's concentrated or dilute. Now we end up with an alcohol. If this is an alcohol, this is now hydrolysis. Now that means our base must be dilute. And now there's also additions to this. We can have some mild heat. Okay, we can have alcohol or ethanol as the solvent because it has to dissolve the haloalkane. Mild heat, ethanol as solvent. Okay, great. So these are some of the conditions for this type of reactions, and again, these ones are famous, guys. They have been in the examinations for the past 3 years or so, consistently so there's no excuse for not getting this right in the exam. Now let's go on to the other one. It says organic compound P, the same haloalkane. We are reacting it with sodium hydroxide yet again. Of course, if the other one was hydrolysis, this one should be elimination. Now this one, we see compound R plus 2 other substituents or byproducts, so to speak. Now this means we did indeed an elimination reaction. Now with elimination reaction, we use Zaitsev's rules, ZR, because again it says the poor lose more than the rich, essentially, to get to the major product. Now this is already suggesting that this is a concentrated strong base, and then here we can have also strong heat, and then of course we will still need ethanol as solvent, because that thing is partially soluble in water, so we need it to work because this is an aqueous solution. So we must be able to treat it with that first so that we can react this. Nice. So can you see, guys, this is very good. And again here, an addition reaction here. What did we say here? Hydrolysis. What type of a reaction here? This is a substitution. This is a substitution reaction. So we've got an addition reaction, substitution reaction, and elimination reactions. Very important things. Now, once we have made up our minds about that, we can then attempt the questions. So we're told, is pent 1 in saturated or unsaturated? Give a reason for our answer. Now this gives us the vibes of the first question when we were talking about the hydroxyl group bonded to a saturated carbon. Can you see it's coming back? Now maybe this can actually clarify what we probably didn't understand so well up there. Let's see. It says give a reason. All right. Nice and easy. So what are we going to say? Yes, it is unsaturated. Nice. Now the reason is there is a double bond between 2 carbons in the chain. Sometimes the best word, this is specifically a double bond, but the best way in general, you can say multiple bond. Between 2 carbons within the chain. Within, it has to be within the chain. And of course the chain has to be the parent chain, it can't be the side chain. Okay, again, this is very important to realize that we talk to this when we're talking about the parent chain. Now I'm giving extras so that you can understand this, because you may find a situation where a double bond is put in the side chain and it's not the longest chain. Now, whenever you see that, you can get confused because you see a double bond and you want to aim for it, but it may just be the side branch. But here we hardly use side branches with multiple bonds. But hey, as you progress, you will see these things and you start to realize it's possible. But of course, there's a set of rules that are going to be set up for that to be nice. Now, can you see, guys? This double bond must be within the chain. Now, this can explain why, because alcohols are nothing but alkanes where a hydrogen has been substituted for a hydroxyl group. And that means all the carbons in that chain are saturated. So probably that is the implication. Now we can be safely reassured that we chose the right option for question 1.1 in the MCQs. Nice and easy, folks. So we're going to get 1 mark for this and then 1 mark for the the justification. Because when we are told to just give a reason, it's usually just 1 line and that's it. 4.1.2. What are we doing? Well, we're told to write down the type of reaction. I like this statement, but sometimes it's misunderstood by many, including the writings themselves, the textbooks, the study guides, the exam guidelines, the teachers, the examiners. They don't really place particular emphasis on what do we mean when we say type. What do we mean when we say general name? What do we mean when we say specific name? They just seem to get confused and take these as synonyms. Not necessarily. But these are close associates for sure. But we need to be able to separate beans from peas, because these may look similar on the plant when it's still growing up, but what we harvest is different, isn't it? Be very careful. So let's see. A reaction 1. We need the type of reaction 1. Can you see we knew it? The type is the addition reaction. Okay, but now what would be the name? We added a hydrogen halide. So this is halogenation. Now you will find the memorandum saying this nonsense. Remember, the question was clear. The type, now this is a general type in my opinion. So it's an addition reaction. It's not hydrohalogenation. No. No one asked us what is happening in that reaction. We just wanted to classify it in general means or general terms. But if someone asks what exactly is going on in that reaction, we are hydrohalogenating an alkene. Now, and you see, now that is rather more specific now. And that was not the question. But of course, you find the examiners or the memorandums or even the guidelines saying, okay, all right, okay, you get a mark for this one. But I feel like if you're saying hydrohalogenation, you are actually not giving the answer that was being looked for. You are just showing us that you know more, but you're not really answering the question, you know. It's more like someone is asking you, do you know Zama? And then you go like, oh, that guy is a doctor. I mean, that was not the question. Yes, he is a bloody doctor. Maybe even a worse one. But the reality is that was not the question. We didn't ask about what he is. We asked if you knew him, that's all. The answer should have been a simple yes or no. That's all. Yes, I do. Oh, okay, yeah. Somebody can elaborate. Hey, that guy is a doctor, you see. And now, but that guy is crazy, you see. Then they will start debating about that particular aspect that now becomes the next topic to discuss. But the first question had nothing to do with what he is or what he does. It was all about, do you know him or not? So learn to answer the question being asked. Don't give information that is not asked. But at times when you are not so sure, as you saw when I wasn't too sure if I'm saying enough, then add additional information inside brackets, because you're also protecting yourself from being victimized should that not be the requirement. By putting it in brackets, you're also showing that it's of a lesser priority than the first statement that you put forward. Okay, that's another thing. So please guys, these notations or patterns or what, they need to be understood and understood well. I'm saying these things because ndijengoTata omkhulu wazawumane ephinda-phinda into eyi-1 ngoba ndiyanazi aniva nina. Okwesibini, I know but most of the time, most of you are misguided, you see. So I have to ensure that I make up for that misguidance. But at the same time, I might just be misleading you too. You need to be very careful. The thing is, I don't read your exam guidelines per se. So I don't even waste my time going there, because even when I was a matriculant, I never read those things. I never cared anyway if they existed or not, because I knew how my teacher is teaching me. It's exactly what I need, because they're teaching within the curriculum. Okay, now when my teacher feels he needs to add something extra, it means he sees that there is an opportunity for that even within the curriculum. So it wouldn't be regarded as wrong, because they have experience of years of teaching the same subject. You understand? So sometimes you need to trust your teachers more than that document in isolation, or in fact don't even try to go against your teachers when they seem to maybe add more to what would be on the guidelines. If they add more, they're just trying to show you there's opportunity for that being put to use, and there's no harm that can be caused about it. And in fact, it might just be a huge advantage for you going forward. You understand? So it's very important to know those things, but don't attach to them. They are mere guidelines. They are not rules. Those are not exam rules, folks, please. Exam rules is the instruction for that particular question paper. If you adhere to those, even if you bend those guidelines, no one is going to take you down. And if they do it, call me. I will be your advocate, okay? And I'm meaning it. I mean what I'm saying, guys. I'm serious, actually. It's not a joke. I can take anybody on this issue all the way to hell and back, kicking and screaming and all matters, all manner of things. So it can happen, okay? So don't be afraid. Okay, let's not talk too much. Reaction 3. Now, what is happening in reaction 3? It's an elimination reaction, because we could see now that, okay, it's eliminating more, then definitely we're not really substituting, because when we substitute, we are likely to form 2 substances. But once we have another extra one, it means we took more out, right? Right. Now, this is clear that we have done some elimination. Now, folks, let's have a look at this. Now, I know again, here I find people saying, what did we do? Sorry, we removed the halide ion together with water. Can you see that? So we basically dehydrohalogenated. Halogenation. Again, you will be told this is fair, but I think it's absolute nonsense, because yes, you know what is going on in there, but that was not the question. The question said, classify that reaction. Didn't say tell us what is taking place there. See, there's a difference in the line of questioning, and even the way of questioning should always be very clear. That's why also examiners have a job to fulfill here, to ensure that when they ask questions, they are being specific. You can't get 2 ideas for 1 question. The question has to be clear. Then if you're going crazy, then you're going crazy on your own. And that's the job of the quality assurer as well, to ensure that when they look at those questions, they need to think about it. What would an average student, how would an average student respond to such a question? Is that question clear enough as to what it requires? And also they look at the quality of the answers provided by the examiner. Are these fair? Because sometimes you can see others are too deep, you see. And would you really expect an average student in some rural area where there's no science lab, there's no science teacher, the teacher who teaches science is actually an English major who just found the job because that was the vacant post available at the school, and now they're learning the science on the job? Obviously, those kids are compromised, folks. Now we have to think about these when we also assess the quality of the exams we are giving. We shouldn't be proud, our exams are up to standard, but we don't cater for the ones who are actually in a poor situation, and only because of this unequal distribution of services for education in this country. And this has nothing to do with privilege and what. It has everything to do with mismanagement by the governing bodies or the authorities. And so they are to blame, not anything else, okay? Those who are privileged are good because they can make it for themselves. There's nothing wrong with that. But those who are not, unfortunately, it's a sad situation. But who is to blame? The very government. Who? The very parents themselves are to blame. You know why? Why would you have children that you cannot look after properly in the best way possible? What is your drive? Of course, it's different reasons. Others, they know, I need children to look after me when I'm older, but I don't have much. But those kids have a potential to become better than me. Now, if you raise them well, you do well. Trust me, even if you are poor as a parent, your kids are going to become whatever they want, and they can actually improve your home situation. So now, if you're going to have a kid and you don't have much, you didn't do much, make sure you raise them well, because if those kids are principled, they will be brilliant automatically. Because once those kids are principled, brilliance is easy, it's effortless, it can be learned, remember, as much as it can be a natural quality of somebody, but that can be lost without principles. And in fact, those who were born without that much, talent, but skills can be acquired, because you only acquire skills through being principled, because it means you're going to be disciplined enough to acquire those skills and use them appropriately. So now when things don't go so well, again, we can't cry, because it was the choice of the parents. So you see, the people to blame here is the parents and the state for the issues of unequal distribution of services for education. It is to blame. There's no question about it. We have a lot of rubbish soaps on SABC 1 than we have educational programs, and that makes me sick to my core. Because when Mr. William Smith and the team, Moira, Stacy, what was the lady that was teaching biology? Oh man, I actually had a crush on that one. Oh, she was blonde, man. Yeah, I like those ones. And I saw a bit on was it African Magic? I don't know, but there was some other educational program where I spotted her teaching biology. You guys call it life sciences. Oh, that one, telling you, man. I'm telling you, man. But anyway, it was older, so it was not possible. Anyhow, those guys, there was more education than the stupid things. Now you have celebrities and doing all sorts of nonsensical games on TV. And then immediately after that, in the evening, there's all of these rubbish stories they call our stories. Those things are not our stories, folks. That's an insult to our image and dignity as the people of this country. We didn't fight for this nonsense to be spread around, kids being exposed to absolute rubbish rather than things that improve them. Now we cry when kids in different areas and parts of the country, now we have electricity. This was the best opportunity to have these programs. SABC 1, 2, 3 should actually have programs running there. Because again, we can't prioritize only the STEM subjects. What about the others? Because other kids are measuring in those. Now these different channels should actually be, maybe SABC 1 at a particular time interval, we know that it specializes with maths and science. Then SABC 2 would be doing like the economic things, and then 3, the histories and the others. But we can't have these stupid talk shows that actually are destructive to our society being prioritized. And then we wonder why certain provinces don't perform so well. Because, those are already poor people in those provinces. Isi is one of them. Even though there's electricity, but some homes don't even have a TV. So now you see, those that actually can have a TV, again, there's no programs, because now they have to buy data. Those people already don't have money, guys, and you know what, it's sad. So I'm not happy, folks. I'm not happy, but it doesn't matter anyway. I don't even know what I was trying to say now. See, I kind of lost my train of thought because of talking the feel. You see, maybe it's better to do what? To clap me. Maybe I'll start focusing. All right, okay, all right. So we did it. So what I'm trying to say, guys, please be particular about these questions, because it's easy to answer nonsensically and in a way that is acceptable. But remember, if you learn to not say the right things, then you'll always say, things that are beside the point and not on point. See, this is the kind of people we have as our leaders in society. I don't even know why we call those fools leaders, because they're not leading anything. They're just filling up spaces instead. In fact, they're just blocking. These are antagonists. You will learn something about receptors in the body. When you place something on the receptor to block the right, molecule to bind in there for a proper effect, and then you put the wrong one and that blocks that effect, it leads to disease and malfunction, or at least dysfunction. Okay, now this is the situation we have. We have receptor blockers here, because they appear to be the right individuals for those positions, because we have nothing better than them anyway. But here's the problem. We're not getting anywhere as society, because remember, we need signal transduction. It has to come from the outside in. And on the inside, there has to be a cascade of reactions and productions of substances that later on, when we export out of those cells into the system, then they have a lasting and a greater effect in the entire body. Things like hormones, you see. If, for example, someone is under stress, then there will be a signaling in certain cells to produce cortisol. And then the release of cortisol will be weight needed, because that means this is high energy state expenditure. So we need to mobilize things like, glucose, and then we start to do glycolysis, or gluconeogenesis, you name all of these substances. But at the end of the day, what is the goal? Is to raise the substrate for energy expenditure, so that we can withstand that stressful situation as long as it wants to last. Okay, of course, when it goes to pathological level, then we fail the test and we start to suffer a disease which needs more attention, and it can be precarious. So this is the situation, guys, in our land, and I am not very happy about it, but hey, it's the way it is, and hey, I am not going to be able to change it, even if I talk too much. Remember, nobody listens to an individual, but people do pay attention to a group of individuals who seem to say the same thing. And of course, we need to also assess, why are they saying those things? Is it me trying to make myself popular or sound like I'm more educated or what? No, it's me trying to have a situation fixed, because I have suffered under the same conditions, but thankfully, there was enough support for me to outmaneuver those limitations. But how about those who cannot? Are they supposed to then fall into the cracks? No, we need to rescue them. All right, okay, so sigqibile la question ne senthethe kakhulu, andisazi noba ndithethele ntoni futhi. 4.1.4. My student is waiting for me, guys. I'm going to have to cut this video here, and then I will do the others sequentially. Now write down, wait. It says now write down the structural formula of compound P. Nice. Now we're talking about rich getting richer. So first of all, pent 1 in is 1, 2, 3, 4, 5. Now pent 1 in, it means the double bond is there. So there's going to be those ones like that, like that, like that, like that, like that. Those are hydrogens. So that would be pent 1 in. Now, when we bring in the hydrogen halide, can you see? We said the richer will get richer. So that means the hydrogen is going to add there. Whereas this one, which was poor shem, it stays poor. Okay, by nikeza idamu uthi ncelala aphume nobisi lapha, but yancela ingane nayo bese yathula shem shebet. Kaze kuzophuma ntoni? Maybe ixilongo solivuthela bezwe bonke ukuthi sesiyakhalaza ke manje, sesikhathele, asisakhoni. Anyway, anyhow, structural formula of compound B. Now we can see this is the situation. 1, 2, 3, 4, 5. So this one is going to carry more hydrogens, because the carbon that was carrying more hydrogens of the two that participate in the bond is going to carry the extra hydrogen. And then the carbon that carried the less number of hydrogens will then carry the substitute. Okay, now that's what we have. Okay, that is it. So this is basically the haloalkane. All right. So we can call this one 2-chloropentane. Nice. So this is a secondary haloalkane, because this is a secondary carbon. Why? Because it is bonded to 2 other carbons in the chain. Nice and easy. So we've done it, guys. So what is most important here is the position of the haloalkane, because it is the functional group. It must be on the secondary carbon, which is the second carbon here, and then the rest of the chain. Nicely. So 4.1.5. says now the IUPAC name of compound Q. Now compound Q is the secondary alcohol. So obviously we took the same molecule, but this time we're going to replace this halide ion with the hydroxyl group. Right? Right. That's it. That's it. So we're doing a substitution reaction here. Can you see that? Great stuff. So what are we substituting? Remember, we're substituting the chlorine with the hydroxyl group. And that chloride ion will pick up the sodium from the sodium hydroxide to form salt. So that is all that we see. Now we're going to write this one out. So this is on the second carbon. So this is again pent. So now this one is going to be penten 2-ol. Penten 2-ol. So again, the position of the hydroxyl group, the functional group, is important here. How many marks are we scoring here? 2. Okay, maybe the parent chain, but again, not really a big deal. So we've got 4.1.6. Now 4.1.6 says reactions 2 and 3 require use of strong base. Yes, we saw that. Write down the conditions that will prefer reaction 2 over reaction 3. Now reaction 2 is the hydrolysis. So what do we need? Mild heat. Because a strong heat will cause an elimination. 1. 2, we need a dilute strong base. In this case, it's sodium hydroxide. Now, of course, guys, the third one is not really important because it favors the other one. So do not find yourself writing this one. Ethanol as solvent. This is dangerous territory. Do not say it. Why? Because it applies to both. Now we want what will favor basically reaction 2. So these are the only two. Okay. So again, guys, be very careful of what you write. It's so easy to miss the point. It's so easy. Because if you start saying things that are not necessary, if you don't assess the quality of those things. So this as a solvent is the solvent in both reactions. So we don't want what goes into both. We want what separates the two. What separates boys to men, what is it? What is it? Imisebenzi, guys. It's not uyentabeni, ubuye nje ubhayiza. No. But ideally, though, uyentabeni was the best way to do so because it means you have run through some tests. You have been tested and tried. And so you are indeed at a basic level a man. But now there's fucker. Yo. I sneezed, guys, I'm sorry. But those people who go there nowadays are children who just don't grow up. They think going there is what we can eat at the end of the day. No, it doesn't. Yes, it can be, if only those people are responsible enough to use it. But now they are not responsible enough. They go around talking nonsense, thinking that is what matters to the rest of the country. It does not. It only matters in their communities. Even there nowadays, it has lost its luster because essentially those people are disgraceful. Let's just speak the truth as it is. So now it has nullified the value of the tradition itself. Anyway, I wish we can go back to respecting our culture and not just respecting it by trying to see or make the world see us perform it, but we want to respect it by abiding by its precepts because there are certain responsibilities that come with that kind of behavior. And that sort of expectation is for the greater good, not for just individualistic perspectives, choices, and preferences. You know what? I can say a whole lot of things and still not mean anything. You get me. Anyway, now pent 1-ene and organic compound are isomers. Yes, because we saw that technically This is an alkene, and if we eliminate, we're going to form an alkene. But now what happened to the bond? This one is an alcohol. So that means O compound Q, no, O compound R came from compound Q. Now compound Q was like this, 1, 2, 3, 4, 5. Now there was an OH here. Of course, seeing that there's hydrogens everywhere. Now when we eliminate, we are going to take this dude for sure, because it is easy to target, isn't it? But now who is going to lose? Now the richer ones are saying, thank you very much, we are not willing to lose. Now the poor ones are already vulnerable, so thieves come for them. So they will eliminate. The thieves are going to come and steal that hydrogen over there. That is Zaitsev's rule, all right? And then that will form the water, which is this byproduct there. Okay, so that means the bond is going to move here now. The double bond is on the second and third carbons instead of the first and second carbons. So that is the most important. So it says, what type of isomers is pent-1-ene and organic compound R? We can see that these are positional isomers because we saw that the double bond was in the first and second carbons. Now it's in the second and third carbon. So it's the position of the double bond that has switched. So these are positional isomers. Sorry, not this one is positional. Okay, so this is positional. Now it's important to notice that this is 2 marks because can you see we needed to first think about where it came from and how it came about. Very interesting stuff. Now 4.2 says, the flow diagram below shows the conversion of butane 1-ol to butane gas. Now we've got butane 1-ol, and then step 1 we've got an organic compound X, then we don't know what's cooking, then to butane. Very strange stuff. Now we need more to understand what's going on. It says the following chemicals are needed. Sulfuric acid. So what do we understand sulfuric acid to be? A dehydrating agent. So obviously, who are we going to dehydrate? It's an alcohol. We can do that in the alcohol. So these ones go together. That means that makes up step 1. We dehydrate this into an alkene. So this means this is going to be an alkene because it's an elimination reaction. That's step 1. Nice. Now with an alkene, we can then add hydrogen to it. So we are hydrogenating it. And of course, usually we do this in the presence of a catalyst, platinum. So this is nothing but addition reaction. And specifically hydrogenation. Now we can understand what we are dealing with. Now that we understand what we are dealing with, we can answer the question. It says now using condensed structural formulae, write down the balanced equation and indicate the chemicals used in each step in the preparation of this one. So of course we've got 2 steps, so we can write step 1 is like this. Now condensed. Now pent-1-ene, because that is the one. No, butane 1-ol, sorry. So this is going to be 1, 2, 3, 4. Butane 1-ol. This is the one. Hydrogens, and then of course they continue like that. Now, what is the condensed structural formula here? This is CH3, CH3 condensed. We sometimes do the CH3, CH2, CH3, CH2, CH2. And then this is CH2 OH. Nice. So this is what we have. So 1, 2, 3, 4, yes. Now we were told to use condensed structural formulae. So maybe let me try and move it a bit so that I cannot lose too much space. Then what are we going to do? Remember, when we're using sulfuric acid as a dehydrating agent, we don't really use it as a reactant. It is on the bridge. Okay, acts as a dehydrating agent, as a catalyst at the same time. But now for us to eliminate, we sometimes use heat. Okay, strong heat as well. So that triangle represents heat. This is another thing that is hidden. And then what are we going to get? Now we will lose this thingy here. So if we lose this one together with this hydrogen, because this is what we're going to end up losing. So when we lose that, what do we see? So there's going to be a double bond there. So what we're going to end up with, maybe let's just do this. Oh, my student is probably panicking by now. Okay guys, I'm going to cut the video at the end of this question to avoid my student waiting forever, and also to avoid giving you a very long lengthy thing. These are the most marks. Please focus on this, then I will do the rest of these questions as the day progresses. I just hope they find you in good time. Now let's have a look. What are we going to have? Okay, so we're going to still have CH3, CH2. This time it's going to be just CH, CH, 2. Lovely stuff. Because now what are we going to have? We're going to form this double bond there. When those two disappear, now can you see? So we'll have CH3, CH2, CH, CH2. That's what we will have. But now what will have come out? Water. Okay, nice. So remember guys, the inorganic molecule, we don't write a structural formula for it. It's not organic chemistry. So when we are dealing with organic chemistry and we have to do structural formula or condensed, we only focus on the inorganic molecules. Sorry, on the organic molecules. The inorganic, we use molecular formulas, standard. Unless otherwise stated that for the inorganic molecule, please also, but I don't think it's necessary because the section itself demands otherwise. All right? Okay. So don't find yourself wasting your time trying to write a structural formula for this. This is not chemistry grade 11. Yes, I'm saying it. Now let's do it. Step 2. The step 2 here. Step 2 here. What does it say? Now this form is the one that starts the things. CH3, CH2, oops, what am I doing? CH, CH2. Now what are we doing? We are adding hydrogen gas. So this time we will add it as a reactant. Hydrogen gas. Again, we write the molecular formula for the inorganic component. Then we go on. Yo, yebafet. So this is in the presence of platinum as a catalyst. We show it on the bridge, and there's going to be heat as well. Okay, good. And then what do we get? An alkane this time. CH3, CH2, CH2, CH3. So we get butane. Now that is essentially what we will get, folks. So this is a mark, this is a mark, and the requirements. This is a mark, this is a mark, and the requirements. So that amounts to 6 marks. And that could be a very nice 18 marks if you know your work and enjoy it, provided you have been taught well. All right. Now, folks, I need to cut this video here, and I'll post this portion for you guys to look at. And then the next video, which I will hope to try and push in between the lessons with my student, is going to be 5, 6, 7, which is the big boys. And maybe I'll just do 8 and 9 as well, so that we can just end it. So I'll try to do those questions in a streak on the next video. Hopefully this will be entertaining enough for you to revise fully and well. Otherwise, I'll see you shortly. before the day ends. And I'm sorry guys, my time frames have been very hectic. I couldn't do as I need to. It's not my style to give you things in the last minutes, because I don't believe in that. But unfortunately, circumstances put me in a different position. Now, to keep up my promises, I have to do this. And I'll still do the acid-based questions that were asked. I'll try to do them individually. And I just hope they will reach you guys within reasonable time. Make sure you sleep, preferably 11 p.m. The latest should be midnight. Okay, because you need those 6 hours of sleep. You need to wake up fresh before you write that exam. You can't do the cross-nighting. Please don't do it. Alright guys, I'll see you again in the next video, because yeah, unfortunately I cannot finish this one nicely. Alright guys, so unfortunately my student and I, because it's rambling outside, she couldn't hear me properly because there's lots of noise. Now we kind of took a pause, so let's carry on so that we don't lose this video also, because I figured to cut it, it would not be good. I would rather just do it all so that you can pick what you like and use it. Now question 5 says the reaction between excess hydrochloric acid with zinc. So what does that make zinc? You know it. This is the limiting reagent. Meaning it gets used up. Completely during the reaction. Now, is used to investigate factors that influence the reaction rate. Now, the balanced equation is this. Now, I always classify my types of reactions because for me, it helps me to make sense of the situation. For example, usually they like to choose spontaneous reactions for this, because something that already needs heat to take place is not so good. And hence you will see that actually the delta H is negative. When delta H is negative, it means this is exothermic. No? And exothermic reactions are all spontaneous reactions. Okay? Now, what examples do you have of spontaneous reactions? Is acid-base reactions and redox reactions. So most likely you will see something like this. You will see an acid-base reaction used or a redox reaction. But sometimes they can use things that have reversible reactions, because again, these very same reactions we chose are effectively reversible if we create a closed system. But in an open system, they tend to go in one direction. Okay, that is what you need to know. So now what is the reaction here? Zinc has an oxidation number of 0. Hydrogen here has a plus, the chlorine has a negative. Zinc has now acquired 2 plus because the chlorine is a 2 minus now. Sorry. And then the hydrogen in its natural state is 0. So can you see zinc from 0 to 2 plus? That's an increase in the oxidation number. So what does that become? Oxidation. H plus, from H plus to 0, that becomes it becomes a reduction, because that's a reduction in the oxidation number. But as for the chloride ion, it remains a minus on either side. So we call that one a spectator ion. All right. So this is nothing but a redox reaction. And it's rightly so, because we need a spontaneous reaction so that as we tweak these other conditions, we can then determine what influences the reaction rate. But those non-spontaneous ones that need heat, then we can't use heat to determine how this reaction is going. Can you see? So these are some of the things that one needs to consider. Of course, it's not really too much emphasis into this, but I can tell you there's a lot that you can gain from this as you move along the science. Now, 3 experiments are carried out and 1 factor is changed in each experiment. Okay, now one factor is changed. Now the same volume, see that? Same volume of hydrochloric acid and the same mass of the zinc granules. Can you see? These are the controlled variables so that we can assess this other one. Are used in each experiment. Now the hydrochloric acid completely covers, meaning there's no portion of the zinc that is not covered, meaning which is not reacting. So meaning all the zinc reacts in each experiment. Okay, that's the important thing also. The table below shows the reaction conditions. So experiment 1, we've used 0.5 mole per decimeter cubed of HCl and no copper. Now the other question is, what on earth is this copper doing here? So we saw that the reaction is between zinc and the hydrogen here, with the chloride ion as a spectator. So copper is certainly going to be of the function of a catalyst. Okay, good, because it does not take part in this reaction. So its inclusion is deliberate, but just to, show us some of those dynamics when we add a catalyst and stuff. Now let's have a look. Reaction 2, we've increased the concentration and essentially no catalyst. And then reaction 3 is the same as the concentration in 1, but with a catalyst. So can you see these reactions are comparable? Okay, while these ones are also comparable. These two are comparable in that with those two we can compare them because the only difference between them is that the concentration is changing, and these two are comparable because the only change with them is the presence of the catalyst. All right, so be able to look at these trends and see which ones are you likely to compare nicely. But you cannot compare, for example, reaction 2 and 3, because that one is a danger. It's danger gevaar riding. You can perform no comparison there. Why? Because this one is high, but we don't know how high. This one is also high, but we don't know how high. And can you see there's two things changing here? First is the concentration, and now there's a catalyst. So can you see there's two variables that are changing between those two? So this is not a good comparison. Please don't find yourself trying to do it. You need extra information before we can try our best to see what is going on in there. All right, now let's have a look. Define the reaction rate. Very easy question again, so let's go for it. So this is 5.1. Actually, we start by writing question 5. Okay, so follow the instructions, please. So what is this? It is the rate of change. Since we are looking at concentration, we can just say concentration of reactants and or products. Yeah. Once we use the word rate of change, we're already saying it's the change in concentration per unit time. So this is it. It's as concise as you can ask it. Very easy. All right. Okay, all right. Of course, sometimes the best one is to say the reaction rate is going to be the change in the amount of substances, because it depends on how many they are and which ones are changing per unit time. Okay, so so the amount can be number of moles, can be mass, it can be concentration, it can be volume if gases are involved. Okay, so there's plenty of things we can look at nicely. So just describe that in words. Easy. 5.2 says, write down the investigative question comparing experiments 1 and 2. Can you see? We saw that indeed we can compare those two. We can also compare those two, but we cannot compare these ones, 2 and 3, at least at this stage. So what would be the investigative question? The key is the answer to that must not be a no or a yes. it has to be an argument, it has to be an experiment, it has to be a discussion of some sort. So that is the scientific question. Even when you do research and you're doing your proposals, these are the things that one has to make sure are cooking. All right, so the investigative question, you can say here, how does a change of concentration, for example, affect the rate of the reaction, the rate of the reaction, right? Yabo, because what changed between 1 and 2 is the concentration, and hence you need to be particular. If you start talking about other things, you get penalized because the question was specific between reaction 1 and 2. And you can clearly see here, there is no way you can answer this with a yes or no. You would truly be stupid if you do that. Right, right. So 1 mark or 2 marks, nice. So this question is often common as well. Be in a position to do it. It's been quite repetitive. Now the curve not drawn to scale is obtained for the volume of hydrogen gas. Can you see? This is what we're using as a surrogate measure of the reaction rate, so to speak. Hydrogen gas produced over time for experiment 1. Very careful. When there is a particular emphasis or rather mention or relevance to a particular question. Guys, I apologize. There's rain now. It's heavy. And there's thunderstorm outside, so there's lots of thunder. So if this is destructive, I apologize. But it provides me an opportunity to finish this paper for you guys, and so you can get it within reasonable time. Okay, I would advise you guys to watch this video. Literally, if you've been practicing now, because it's gonna come up late, I would rather you watch this video when you have finished what you wanted to do. Then you want an overall review and all the techniques and tricks to deal with questions and how to answer appropriately. This can become an overall review. That is something you can even watch lazily like a movie, okay? I would advise you to do that. But if you're still struggling, guys, whatever means necessary, just pause the video, attempt the question, struggle, then look at what I'm doing. But then this is going to take a bit of time, and that would mean I'm most likely to just use this paper only as a revision device, so to speak, and then after which you can do whatever you still feel you need to do. But it's not the best approach. The best approach at this moment would be to do whatever you need to do as much as you need to. Then when you want an overall review, you watch this video from beginning to the end. I can assure you, sometimes a way of using the resources is what matters than just using them anyhow. Okay, now let's look at this experiment. What do we see? As time passes, this graph plateaus. What does that mean? Now we didn't see any equation that is reversible. So this means this reaction has come to an end at the plateau. Obviously so, because the collision theory says as we use up more of the reactant particles, their concentrations drop. And as the concentration drops, the reaction rate drops. Because the gradients here represents the reaction rate. Right? Because the change in Y over change in X. So you see the gradients are changing, and then here it's flat. So this is the understanding. And then of course, this would be the volume. You see, this one is not labeled. So someone can say, provide a suitable level for the y-axis. This is the volume of H2 gas. In what units? Now we will have to see more, because at the moment we cannot be too sure of the units. Okay, because there's not enough given to us. But time, if it is not stated, we will assume seconds. It's easy to do that, because the unit time in physics or in chemistry is nothing but seconds. But it can be something else. Be on the lookout that you're not overly assuming and overly projecting, but at the same time you're not really staying far off. But volumes can be different. That's why we hardly have a single measure, but with time we tend to have a single measure. Now it says, how does the rate at which hydrogen gas is produced between T1 and T2 compared to between T2 and T3. And as we can see here, guys, the gradient here is much steeper than the gradient over there if we say average. So it is higher than, because this is T1 against T1 to T2 against T2 to T3. So it's going to be higher than. So it's 5.3.1. We're going to say higher than 5.3.2. Now, of course, sometimes you may be asked why, because the gradient is less steep between T2 and T3 than it is between T1 and T2. You just use the gradient on the graph. Or they can say what evidence on the graph is responsible for your choice. Then you give it to us. Okay, all right. Sometimes they can explain that very same reason for the gradients to drop, because as the reactant particles are used up, their concentration decreases. And so we know that reaction rate is directly proportional to the change of concentration of reactants, and so it will drop as well. So these are some of the things you want to actually play around with, because this is how the examiners play around with you with the science here. Okay, that was just 1 mark. No explanation, but remember, in the final exams, expect 2 follow-up questions. Say what evidence on the graph is responsible for your choice. You choose that the gradients are steeper between T1 and T2 over T2 and T3, because that represents the reaction rate, number 1. Now the follow-up question to that can say, explain your answer fully, okay, using the collision theory. You see that? So drop of concentration means less particles are available for regular and effective collisions, and therefore that would mean the reaction rate drops. Easy stuff. So that is how you go about things here. Now 5.3.2 says redraw the graph in the answer book and clearly label the curve as A. So I'm just going to label this one as A. Now, on the same set of axes, sketch the curve that will be obtained for experiment 3. Now we can see 1 and 3 we can compare. This one is going to be faster because of the catalyst. So it means its gradients are going to be a lot steeper. So we'll just see something like this. But it has to plateau the same way. Okay? Starting from the origin, of course. But now this was a drawing, so we need to break it up. Okay, good. So this means this one is a lot steeper. The gradients are a lot steeper than the ones over there. Okay, that's just the idea. That means we achieve the peak. Maybe maybe this is not a correct representation actually, guys. Now we need to make sure that we don't get to the plateau at the same time. It has to be at an earlier time. So maybe let's make it a lot steeper. Yes. Now that is a lot better. That is a lot better. I don't know. This thing is trying to make me angry. And I'm going to get angry actually when it wants me to. Alright, okay, alright. So guys, the most important is to ensure that this thing here joins. Sometimes it's not going to be perfect, okay? But just make sure it joins. That's what matters. Alright, okay. And therefore we can label this one as B. So we get our 2 marks. And you see, when you understand these things here, the kinetics here, molecular kinetics. Anyway, that's it. Easy 2 marks. So here I can just refer you to the sketch in my video, of course. Now 5.4. What does 5.4 says? The reaction in experiment 1 takes 58 seconds. Can you see now we're given time to reach completion, and the average reaction rate which hydrogen gas is produced is, again, we're given that. Now can you see? This is centimeter cubed per second. Can you see that? So that means on the y-axis we've got centimeter cubed. So now this would be a very good question to say, what are the units? Or what would be the appropriate units for the y-axis? It's going to be centimeter cubed. We are reading it from here. And what would be the appropriate one for the time axis? It's going to be second, because I said per second. Didn't say per minute or per hour. You see these things. So sometimes more information is necessary to respond to yet another bunch of questions that can come. Now it says calculate the initial mass of zinc used in each experiment. Okay, good. So now this one is always there, guys. It's always there, and it's usually around 5 marks, 6 marks, sometimes 7 marks. It's a higher grade question because it's one of those back calculations, so multi-step approach. Now let's have a look. We know that the reaction rate is going to be the change of volume, because we saw that this is now volume, right? Change of volume over change in time. Now this is 8,39 equals change of volume is what we don't know, and the time is basically 58 seconds, and so that is over 1. So we cross multiply here. What do we get? Therefore the change in volume is going to be 58 into 8 into 8,39. Okay, that is nice. Maybe let's just say that implies. So I want to say something different. Therefore, remember the volume produced, volume of hydrogen gas produced, because the change is exactly the production, because it's from 0 to some big value. So actually that's what we produced. So it's very important to know how to, modify these things as you go along. Again, guys, this requires skill, confidence, and proper teaching and training. If you don't have any of those, it doesn't matter what you do. You will keep getting stuck. Now this would be centimeter cubed. Nice and easy. So what are we getting to? Well, if we know the volume, we can then calculate the number of moles in the equation. Right? Right. But now what we can say is, we know that 1 mole of zinc produces, or you can say yields, maybe that word is much simpler. It yields 1 mole of hydrogen gas from the equation, right? 1:1. So this implies the number of moles of zinc used, let's put it nicely, zinc used is going to be equal to the number of moles of hydrogen gas produced. Nice. So this implies that the number of moles of our zinc is going to be, now it's going to be volume over the molar gas volume. Actually, we didn't read that statement correctly. We're told the molar volume of hydrogen at 25 degrees is that. So always be on the lookout. When it's not given, we'll be told STP, in which case that would be 22,4 decimeter cubed. Yeah? Remember that. Now, we substitute. This implies that the number of moles of Zn, KwaZulu-Natal, so this is going to be 486,62 divided by, now this is 24 squared, which is nothing but 24 decimeter cubed. So let's see, maybe it's safer to say therefore, so that we can end this pain. So we divide that by 24,000. Sorry guys. So now I'm getting here to 3 decimal places. This is 0,020. Remember, we always protect our decimals by, if we want 2, then we can protect it by taking 3 mole. All right. Now this is good, because now we have the number of moles of zinc. Can you see? With just 1 stone, I hit 2 birds, because instead of wasting time calculating the number of moles of hydrogen and then later on say something else, you end up with too many steps. So find a way of summarizing but not losing the science. But again, guys, remember the approach is how you see it. If you feel that is what you need to do, it's okay. By all means, do it. You will get marks. Okay. Now, What are we going to do? We're going to say then, we know that number of moles of zinc is usually from the mass of zinc divided by the molar mass of zinc. This implies that 0,020 is equal to the mass of zinc, which is what we want, divided by the molar mass. Now we go into the periodic table. Unfortunately, there's no cramming this one. This back and forth, unfortunately, has to happen. So can you see? 65. So we write 65 here. And therefore, the mass of zinc is going to be the product of 65 and 0,20. Let's get it. Times 65. Holy cross. So we get so what do we get? We get 1,3. So this is 1,3. Remember, set minimum of 2 decimal places. We need to see that 0 grams. If that 0 is missing, uzogedla amazinyo yaqala uzoyikhotha eyomileyo into ekhothwayo uzayibona ungayazi. Now can you see, guys, in a very short, concise manner, we have really come to the conclusion of that question. And of course, this is one of those questions that tests your knowledge the highest, of course, because that's why it's a higher grade question. You need to know how things relate to each other and what. Now, so let's do the things that we must do and move on. So guys, this is 5 marks. So how do we score these marks? Well, any one of these ones is important. So usually the formula that answers the question for me becomes priority over the question that is just used as a means to an end. And then of course we will have the answer here. The substitutions per se, maybe we can entertain them somehow, but I don't think they're that important, because what matters here is this volume, right? And the answer. So already 3 marks. And of course this number of moles matters. So 1, 2, 3, 4. Now what would be the 5th mark? The 5th mark, guys, any one of these scenarios here, this setup is cool. So one can say safely maybe substitutions here is much more important, or anywhere for that matter, because substitutions can be marked there, they can be marked here or here. Even this statement could also carry some marks. So when you see 7 marks, don't think you need to do more than this, but it would mean the examiner has recognized the significance of each step and they're awarding a mark for it. Okay, so don't always panic sometimes. If you've done 3 steps for a 5-mark question, usually when there's more marks than that, it means within those steps there are some that are going to get marks as well. Otherwise, sometimes the approach can be crazy. You see, it just is the way it is. Okay, it is the way it is. So 5.5 question says, experiment 4 is now conducted by increasing the temperature of the reaction mixture in experiment 1. So now in experiment 1, remember we didn't have a catalyst, but now we added heat. Now with heat, that reaction should increase as well. Now it says here, how will this change the effect? How will this change affect the reaction rate? It will increase for sure, because temperature is directly proportional to the reaction rate. So this is going to increase. Okay, so 5.6. Nice, guys, just one easy mark over there. Now it says here, explain the answer in question 5.5 by referring to the collision theory. Of course, you don't say according to the collision theory. You just say the essence of the collision theory. Nice and easy. So what do we know? We know that N increase in temperature will increase the average kinetic energy of reactant particles. Okay, that is the first argument. So an increase in temperature will increase the average kinetic energy of reactant particles. Now what happens as a result? There will be more regular. Remember, they have to be regular because irregular ones don't matter. There has to be more regular, effective collisions, okay, per unit time. And then the reaction, you can say hence the reaction rate will increase. Nice. Can you see, guys? Just be brief, be to the point, but make sure the science is captured. Don't faff around here. It's dangerous. Remember, temperature is it's a surrogate marker or measure of the average kinetic energy of the particles, because for these to collide and to collide effectively, temperature imparts energy to these, so they must have sufficient energy. At the same time, they must be mobile, they must move, okay? And that is what is important about that point, hence we get a mark. Then we are going to talk about regular and effective collisions. Essentially, that statement is key also. Regular and effective, because these have to be regular, because something that is irregular you can't measure its rate, so it has to be regular. Secondly, it has to be effective, because those that happen and they are not effective, they are meaningless. Okay, great, nice. So now hence the reaction rate will do the things. And then here you can even say, sometimes, I like to be creative whenever that suits me. You can say particles here or molecules have, okay, you can say more particles will have sufficient energy. In brackets. Okay, now the energy didn't want to fit in, so they will have sufficient energy. Let me try. Okay, you can put that in brackets, because that is also a very strong statement, because only those with sufficient energy. And I think it's a very important statement to also capture, so that we can say with these regular and effective collisions, it's only those that have sufficient energy. All right, okay, all right. So that is the story, guys. And then, of course, we get a mark for that statement. And then, of course, to prove indeed with the conclusion, sometimes it's an extra mark, sometimes it's not. It just doesn't matter. So this was a very nice 16 marks. So usually the question on reaction rates is nothing but an application of chemistry as a whole. As you could see, we went through some different types of chemical reactions and understanding why, the nuances around them, and we're applying collision theories, we are applying, stoichiometry. Everything is there, everything is there. So guys, be on the lookout. These are the questions that you are going to definitely have to dance with. Now let's get to question 6, chemical equilibrium. Now this is one of the beasts, but not because it's too difficult, but because it's so good. Even in real life, most of the things we see, when we talk of homeostasis, this is some state of equilibrium in the body, when all systems are working together instead of against each other. Okay, any change creates a sickness. That is another way of attempting to correct the problem, but it transpires as a sickness in the body. This is when the equilibrium has been disturbed by either an addition or a subtraction of something. You understand? So can you see? All of these things are somewhat applicable in terms of conceptually applicable in many fields in our lives. So somebody may be asking, why do you need to study these things if you want to become a doctor? Can you see now? You would understand now as a doctor that when someone is sick, it's not because there is some bad situation happening. No, it just means the system was disturbed and the body is actually trying to remedy the problem. But unfortunately, because it's an unusual condition for the body normally, then it shows up as a form of sickness. This is why it's not good as a doctor to treat the symptoms instead of treating the problem, because then you will give the impression to someone that I'm okay, and yet they're slowly dying. Okay, sometimes this may be a sign for some serious damage. For example, pain is nothing but a sign of very impending, maybe we can put it that way, it's a sign of impending damage to a system or to a body part, because where you feel pain, it means there's tissue destruction taking place. If it is not already taking place, it's soon to take place, whatever is the cause. Now, if you numb that pain, you're taking painkillers, then you're actually allowing the damage to take place, because now you're just blocking the nerve from transmitting the information that, hey, damage is taking place in there. Now you just want to treat the pain, and then later on you discover, goodness, I have a cancer there, because now there's a cancer pressing on my nerves in there, and also pressing on tissues that are sensitive, and they're sending the signal that, hey, watch out, there's a problem in that area. So a good doctor would say, yo, kasi yam, mqala uzandihlaza ebantwini ababalulekileyo abafana nani. Now nansi into eyenzekayo apha, kuzakwenzeka ntoni ke ngoku apha, kuzakwenzeka le nto efanele ukwenzeka, andisazazi noba bendifuna uthini. Eyi, kodwa ingathi ndiyaguga, shem. In fact, sendiyahlanya guys, I don't know if nina nicinga njani, but ndiyayibona le nto lena, phambana sekundifikela. And yilaa nto ucinga too much ke leya inje vele ligeza. Okay, consider the following hypothetical reaction at equilibrium, or besipha kulaa nto ye-disturbed state of homeostasis in the body. Now you would know that as a doctor, when somebody has a pain, you first want to find out, where is this pain? Then they will tell you, it's in my shoulder. Okay, now you're already thinking as a doctor, you know that anatomically there's bones coming together, separated by cartilage and synovial fluid. Is it a question of deficiency in the synovial fluid, or destruction of the cartilage, or the joint capsule? Is it torn because of probably overstretching, for those who gym and think, hey, everything is all about gymming? Whatever you don't do in a sort of measured way, it's always dangerous. Okay, anyway, now you're thinking, okay, there could be a torn capsule, but again, you can also think of cancers. They can occur there, cancers of bone, cancers of cartilage, chondrosarcomas, for example, cancers of the glenoid labrum itself, sarcomas. And you can also think of like physical damage, be it from trauma of any form whatsoever. All right, then you can also think this could be nothing but a neural problem. Now the nerves, remember, they travel from the spinal cord to distant areas, so the compression can be anywhere in the pathway. It could even be in the brain somewhere, because those nerves connect over one system of nerves until they reach the destination where they're supposed to go. So can you see, there's a whole lot to consider as a doctor. That's why you need to understand these things properly when you are learning them, so that when you start to think of possibilities, it's effortless, it's second nature. Because someone who's going to rely on studies, they say there's a pain there, they do an x-ray. X-ray is normal, there's no fracture, there's no separation of the joint to suggest any ligamentous tear. Cartilage looks okay, there's no erosion or something like that to suggest maybe some, inflammatory process taking place. The range of movement, when they check you carelessly, they'll see, it's not too bad, but there's pain definitely with movement. But now, where is this pain coming from? Now, they'll, take these painkillers, you should be fine. Only to find that you actually have a tumor in the spinal cord, or at least at the exit of the spinal nerves into the respective areas. Now, by the time they discover it, it has metastasized. Okay, those ones commonly do not, but sometimes they can be a nightmare. Okay, because they can erode the bone and cause a fracture and cause instability of the spine. And maybe someone will only notice when they become quadriplegic or paraplegic. That means they've lost the function or the integrity of the spinal cord. And you're like, what the hell? So quit treating what appears to be the problem. Actually look for the underlying reason for what you see and deal with that which is the reason, because then what you see disappears immediately. Again, guys, this is just me to try and emphasize the significance of learning things in this way. So don't listen to any fool who goes around telling you our education system is weak. They're talking nonsense, okay? Tell them that I said so. And if they have a problem with that, they must call me, okay? And we will meet and I will eat them for lunch, breakfast, and supper, if necessary, for many days, as long as I live, okay? All right, let's go on, guys. Enough of the nonsense and the grandiosity right there. You see, I'm a psychiatric patient with grandiose delusions. Now, consider the following hypothetical reaction. So, again, we see that there's 1 mole of gas A forming 2 moles of gas B. So, essentially, we can see pressure can do some damage here and stuff like that. But now we don't know about the delta H here, because nobody said anything. So we will find information to get to that. Now, the data in the table below shows the equilibrium concentrations of A and B at different temperatures. Now, this is going to give us a clue as to what is the delta H. Now, can you see at 200 degrees Celsius, there is how many moles of A? Less moles of A compared to B. So this is suggesting that, oh, okay, all right, okay. At a lower temperature, the molecules of B are more than that. Then this is suggesting that, hey, when this is most likely an exothermic reaction, because now this has favored the products. Can you see that? So it means lower temperature favors the exothermic reaction. But let's not rush. 300, now we increased the temperature. And what do we see? We start to see the concentration of A is increasing. But what is happening to the concentration of B? It's decreasing. So with the increase in temperature, we are decreasing the concentration of products. Definitely, we know now that delta H is definitely less than 0. Because the exothermic, the lower temperature favored the forward reaction and the higher temperature favored the reverse reaction. And that already says an increase in temperature favors the endothermic, and the endothermic is the reverse, because we see the concentrations of A are climbing. Can you see this? This is something you always need to think about. So analyze, interpret, and synthesize knowledge around what you are given so that you respond like a pro. Now, state Le Chatelier's principle. This is again a very common thing. I'm not even going to waste time and state it. But it just says, if a system is in equilibrium and a disturbance is introduced into it, whatever that disturbance is, that particular system will shift so as to cancel the effect of that change or that disturbance until a new state of equilibrium is re-established. So that is the key. Maybe let me write it down. You know what? Sometimes taking things for granted. We think our students actually learn these things, but they don't, because they don't understand what we are talking about. So it says, when a disturbance is introduced to a chemical, chemical system in equilibrium, meaning is polele bafethu, equilibrium, irelaxile, iketlile, ikhutshitse bakalabe, isayikhutshile nyana. Then wa hlahela nthwena ebitswang ka nta, wa itseba nta, tla fihla mono sa ikhutsitse nyana tla sa sefate, kampa hana ba reng ka Limpopo kwana ba re ke setlhare empa setlhare he ka Southern Sotho is medication. Now in Sepedi and Tswana ha ba bua ka setlhare ba bua ka eng by a tree. Okay, so we khotšitše monna tlasa setlhare mane o inwela ha monate ntho tsa hao tse batang ha monate o fihle ntho ene tshwenyang hampe ba e bitsang tshintshi e kene ka hare mona monna e tlo o etsa hore o be e tlo o kwatisa e re ke ibe he jwalo bona e tlo o kgentsha wa bona o tlo dutla that's wrong o tlo tuka mollo wa bona o tlo tuka mollo wa o kwata hobane jwale o senyetsa tjhelete le ho ikhutsa wa hao mona wa bona wa nthola o je le di-cornflakes sharp o tlo ba le matla wa o araba kampa ho karaba physical science paper. Now let us move my dearies, because there's lots of work we have to do. You see that one, we can't stay. There is no way. This guy, okay. When a disturbance is introduced to a chemical system in equilibrium, right? Their system will shift so as to cancel the effect of that disturbance until a new equilibrium is re-established. Maybe let's just say reached. I think it's better because when we say re-established, it sounds like we're going back to that same level, and the idea is we have literally shifted. It's very important to use that word because the equilibrium will shift its position actually. It's not going to go back to that same position. As opposed to the body. Sometimes the body is capable of shifting back to the normal position. Even this system can do it, but mostly it does not go back. But now in the body, we always try to go back to baseline. By the time certain diseases are very bad, they leave your lungs scarred or your kidneys such that you're only surviving with dialysis and stuff. If you've had a liver problem because of too much drinking of alcohol, you end up needing a liver transplant. And if you take a liver transplant, it means you need to take immunosuppressive medications to try and fight your body fighting that which you got so that you can live a bit longer. But now the side effects of those medications, can you see your normal state of homeostasis is no longer the same? Yes, you will assume a similar state, but it technically has changed because now you're living on medication, you have medical checks, and yet you would not necessarily have to live by going to the doctor every now and then. Can you see that? If you don't get it, you get it. If you don't get it, you just do not get it. And unfortunately, guys, akukho nto endingayenza ngaloo nto. Ndingaske nje ndithethe ngayo kodwa ngeke ndikwazi ukuyitshintsha. Now, is the forward or reverse reaction favored at 200 ntons? Yes, is the forward reaction because there's more products over reactants at that low temperature. It is the forward. Aibo, ndikwazi ukubhala guys. Yo, it's the forward. Give a reason for your answer. You can say there's more, or the concentration of products. Let's just write that. The concentration of product, or let's not talk about products, but of gas B. Of gas B, you can say in brackets the product, because you want to say that word, is higher than the concentration of gas A, the reactant. Nice. So can you see, not too many things, but just concise stuff. That's all you can see on the table. So interpret information that is given to you guys in the best way possible. And that means not rushing in answering. Can you see, when we just explored our table nicely, quickly, we have answered so many questions in a non-stopping fashion and non-freezing fashion. Now here we need to choose increases, decreases, or no effect. Again, these are the interpretations applying Le Chatelier's principle, of course. Now the pressure is increased. So it says, how will the equilibrium concentration? Now we need to answer the question, guys. Don't spot. How will the equilibrium concentration of gas A, that is the reactant, at 200 degrees Celsius be affected by the following if we increase pressure at that temperature? Now we can see that if we increase pressure, we will favor the reaction with the least number of moles. Now that would be gas A, so we will favor the reverse reaction. And if we favor the reverse reaction, what happens to the concentration? It increases. So that would be increases. 6.1.4. Now, the addition of a suitable catalyst. Now, a catalyst does not change anything because the reverse and the forward are equal in rate. So there will not be a change to that extent. So we'll say no effect. Okay, so it does not have any effect to the equilibrium state. 6.1.5. Now, is the forward reaction exothermic? Is the forward reaction exothermic or endothermic? And we saw that if we favored the forward reaction with a lesser temperature, then that should be exothermic. Can you see that that delta H we explored comes back to give us the bonus? Is exothermic. So can you see, guys, we're collecting marks there. We're just collecting marks, nice and easy. Now use Le Chatelier's principle to refer to the data in the table to explain the answer in 6.1.5. Can you see? Now we have to apply Le Chatelier's principle, where we talk about a decrease in temperature favors a exothermic reaction. And that's all we need to say, more than every other thing. So let's go on. So now this is one of those annoying questions because you have to now structure your argument. You can't just open your mouth and start spitting nonsense there. Now use the Le Chatelier's principle to refer to the data in the table to explain the answer to question 6.1.5. Now how do we respond to this one? We respond by saying at a lower temperature, the forward reaction was favored. And we know that an exothermic reaction is favored by a low temperature. And hence, the forward reaction is exothermic. So what are we going to say at low temperature? There was more products than reactants. Okay, at low temperature, the forward, let's just not say too much, okay? Let's say at low temperature, the forward reaction was favored. The evidence is by those concentrations, but I mean for 3 marks, we don't want to say too much. And we can say now, a decrease in temperature favors the exothermic reaction. Hi guys, my writing is fading. Therefore, we can say the forward reaction is exothermic in effect. Can you see 3 marks? We could see that the reaction in the forward direction was favored at that low temperature. But now Le Chatelier's principle tells us, now this is the part that speaks to the Le Chatelier's principle. You don't have to say according to Le Chatelier, But if you say a decrease in temperature favors the exothermic reaction, why? Because it releases more heat. That means the disturbance was a drop in temperature. Now, how does the system respond? By generating more heat. Now, it tries to cancel the drop in temperature. Can you see? That's already Le Chatelier's principle. So this is where it comes in. You don't have to say according to Le Chatelier. The moment you say this, you're already speaking the Le Chatelier's principle in essence. Okay? And then, of course, you make a conclusion. So this is the most important part. And, of course, the conclusion has to be there because we need to decide and decide decisively. You know, comrades, Moss, this is the sting. This is the sting that won. This is the sting that I won. I won as nah. So I'm hoping, guys, the revision is going nicely. Now, initially, now siyayazi ba yengo uzawukhala intonga. Holla dintho jwalo, go tlolla dithunya monna. Holla ditshepe, holla diphafa. Holla hana le re ke eng thwena. Sephadi monna, diphadi ke tsona ka mona. Ditlolla. Holla dimpama, holla maquza. Makwai, dintho tsena kaofela di a lla jwale. Ha o sa tsebe mosebetsi wa hao o shwele. Re tlo o pata. Siyagcwaba xa ungasazi isibani sakho. Siyagqiba. We bury you. I don't know in Afrikaans how do you say this one. Now at equilibrium, so we see that this is the same thing. But now it says, okay, let's start talking sense now. Let's not be careless. Initially 0.5 moles of bromine gas. Now can you see this is similar to what we're dealing with. So this was a hypothetical. Now they're bringing in the actual equation. Bromine gas is sealed in an empty container. The following reaction at 1600 degrees Celsius. Can you see? We have increased the temperature because this model we were given actually is similar to this actual situation. Now this is already trying to tell us a story that the forward reaction here is still exothermic. Now the temperature is higher than we were. That means there will be less of this one and more of that. And now we should expect a Kc value that is less than 1. And what do you see there? Definitely. Kc is less because there's more reactants than products. That 10 to the exponent minus 4 is the signature to suggest this is less than 1. Now this is a small yield or a low yield. In fact, we can even say a very low yield. This means this reaction is actually going backward because of this higher temperature. Can you see? There can be a lot of questions one can generate from this piece of information, knowing what we have gone through already. But now that is not where we are. So the question says now, okay, we've got bromide gas decomposing into the bromide ion or halide ions. Okay, now at equilibrium, the concentration of bromine is this one. Okay. This is in mole per decimeter cubed. Now remember, a molar concentration we can use on our table nicely. Now the equilibrium constant is this one at that temperature. Now we need to find the volume of the container. Okay, this is easy. It's not bad. It's not bad at all. Now maybe let's just answer this question alone. So 6.2. What do we have? Br2. Going forward, going backward to give us 2Br. Okay, now they're telling us this is a gas? No ways. Are you serious? Okay, maybe it's an ionic form of the gas. My lord, I've never seen this one. But anyway, gases can ionize, eh? Careful. Ungabi stiff lapho. Be flexible, man, eh? Urobelitheka haiba wakhonahal. Hey, now we can talk about the initial. Now initial here, what does it tell us? So we're given moles. Now we've got concentration and we don't know the thing that we need to know. So now we need to know that thing, which is the volume of the container. Okay. I'm trying to think, guys. Do we then need to convert this to number of moles? Casey gives us this thing. So this is at equilibrium now. How do we plan this, guys? Because in concentrations, but I'm not so sure if it's gonna be the best approach. But now let us try. So we have initial, this is number of moles, right? Then used and produced, that is number of moles. Some people can use just one word and say change here. Okay, remember this is the same thing, but change sometimes, okay, it's nice when you understand it, but this one is much better. On the reactants we are using up, on the products we are producing, isn't it? Equal, we're talking about number of moles. Now we can talk about the concentration at equilibrium. Again, this is good. Okay, so now what did we start with? Initially we put 1, don. So this is going to be here 1,05 moles. Now initially there would be nothing of this one, right? Remember the significance of initial. At the beginning there was the word, and the word was God, and it was with God. Amen. Genesis apho kwaqala khona ekuqaleni komhlaba wayekhona uLizwi, wayenguNkulunkulu, yena uNkulunkulu, konke kwavela ngaye, okudaliwe wadala izulu nomhlaba ekuqaleni. Hey, yawazi ucula? Angazi ucula. Inqandweni gospel group ke le. Ndindivise nje kancinci keyboard yami yofethu. Yabona leni ivideo yamahlanya le. Ayo yabantu abaserious. Hey, ithini? Okay, iqala. Ayisahlangani. Ekuqaleni. Okay, yahlangana. Ekuqaleni. Uvela uqala apha nje. Yayiva yonke seyahlangana. Ay, bese ishaya ibhezi ngoququ. Ay, asivale lezo zakhe before sihlanye kakhulu. Sendifuna ukuhlanya ke ngoba ndisike ndacula le ngoma. Ndahalela ukuyodlala i-keyboard. Yabona nengoma ifumana lula xa uyazi i-keyboard. Awubusokola. Qala nje uthi ufitlishe kayi-1 so itholile i-key. So itholile i-pattern ye-chords omawuzidlala. Then you just spice it with the bass. The bass you can do whatever you want with it. Usually the right hand side press the chords than in notes kwingoma ezinje, praise songs, yabo. Press chords. Nalapho ungapress kakhulu, ungaculi kakhulu ingoma njengoba beyicula. Qala ngokuyifuna njengoba beyicula, then uzawubona biza kulimit because we'll do too many movements. Then it becomes difficult to follow the musicians. Then we start with limit main chords, which chords can actually, capture 2 verses or what 2 lines in a song. Then we call it better pagang we spice it, then manuit. Yayibona yayinyusa yayihlisa ngapha kwi-bass ubetha nje isigubhu ngapha faka i-beat hlangene ingoma, you harmonize the thing. Okay guys, sesihlanyela away, maske siqhubeke ngobe silapha apho besikhona. Now we were told the concentration At equilibrium of bromine is this one. So this is the one right here. 2,074. Now what are we going to say, my friends, is the story. Now we have to be very, very cautious indeed. Because what is the concentration of this one? We can say this is X. If it is X, izospices yabo, izospices masiniye ku X. Maske sithi what we produced is X. Maybe it's better if we say that. And that would mean we used up, maybe let's say 2X. This means we used up X, okay? That is better. Remember, with the change, the mole ratio comes in. We cross over. Nice. So if we say we used up X, then we'll produce 2X. Now at equilibrium, we're just going to have 2X because it's 0 plus X that is produced. Used, we subtract. It's going to be 1,05 minus X. Okay. Now, this is good. Because this simply says the volume here, the concentration is going to be 2X divided by the volume. We don't know it. So that's it. So that's what we have here. Now we can see that expression is going to come in handy. You know. So a little bit of planning, folks, will assist in going about your business properly. So that is V. Now we are ready to start. We know that, okay, all right, Kc by definition is the concentration of the products, but now they will be squared divided by the concentration of the reactants. But that one is to the 1, Now we go on. Say, okay, take us across, sir. This is 6,34 times 10 to the minus 4 is equal to, what is the concentration here? This is 2X over V. And then say squarish over the concentration of the product is 2,074. Yewena, thengathi umnandi kakhulu. Hey, umnandi man, sweet, njengeshukela. Usweet jalo ka tswekere man. Uwalelemela jalo ka metsi man. Yeah. It's all happening here. Now let's go on, folks. What do we know? We know that now this situation here, when we cross multiply 2X over V all squared is equal to. I don't know if it's going to work, but yeah, ingathi izawusebenza 2,074 ne. Yeah. Into 6,34 times 10 to the minus 4. Okay, because guys, maintain vigilance. Now, what are we going to say? Now we keep going, guys. Actually, you know what? I think this is span. Iwari amgeta nunbana nthandabuza ngulo X bandizamthini. Ingxaki yami phaya ukuba la X ndizamthini. Yiyo le ndiphambanisayo ndokuqala. So okay, maske singacingi kakhulu because agqibela sesipayiza. Now guys, can you see that at this step we can even do the gymnastic that can simplify our lives straight away instead of waiting for it? Yeah, this is maths, guys. Mathematical gymnastics. We need to be well-trained gymnastics or gymnasticians, if there's such a thing. So we're going to say square root of 2 square root of 2 to 2,074 into 6,34 exponent minus 4. Nice. So what I'm getting here, this is 0, 0, 3 0.6 mole per decimeter cubed. Okay, I'm feeling cooked, guys. Now, a problem here, we've got two unknowns, folks. We've got two unknowns. Yes, we have the concentration. Inkinga yethu ithi kwenzeke ntoni. Now, ingathi ifuna ukusidefeater because, I mean, it's a very simple calculation, but now we need to think of something here. We need to think of something. We can use this one. Say, Nina, you can help us solve the value of x, isn't it? Now we go on and say, but. So don't panic. When maths tries to create problems, we do it. We know that essentially 1,05 minus x over v is actually equal to 2,074. Well, someone could have started here, someone could have started elsewhere. It's not a big deal. But sometimes I just do it. I mean, this one is evident. You don't need to explain it. Okay, all right, okay. Now we're going to express x in terms of v, because this helps us to then eliminate that x nicely. So this is over 1. So just cross multiply there. When we cross multiply, what we are going to see is that we have 1,05 minus x is equal to 2,074 v. Now what do we want? We want to isolate x. Therefore, x is equal to, transpose it there, we transpose it there. So this is going to be 1,05 minus 2,074 v. Yeah, that's it. Because we transpose x, we transpose that, and then rearrange. So what do we say? We say then we just take it from here. We know that 2x over v equals 0,036 implies that we've got 2 into what is x is 1,05 minus 2,074 v, oops, all over v. This is 0,036 man over 1. So there's a whole lot of cross multiplication here. Yo, why? What is happening here? What is happening here? Yeah, it's all happening, man. It's happening. So simultaneous equations. Remember, guys, the tough questions will always involve simultaneous equations, as you could see it here. However you do your thing, just make sure you plan properly. That's all. So when you multiply by 1 here, what do we have? So we will have, in fact, we need to distribute that one, but it's fine. We can say this is 2 into 1,05 minus 2 into 0,74 v. Not a problem. Equals. Now this is going to be 0,036 v. Right. Now we break this up. So let's do it. So 2 times 2 times 1,05 is what? Is 2,1. Minus, and we've got 2 times 2,074. That one is minus 4,148 v equals 0,036 v. These are like terms. We transpose this one to the other side. So when we add these two, so that one plus 0,036, what do we get? We get a total of 4,184. V is equal to 2,1. Therefore, the volume is going to be 2,1 divided by 4,184. Ntotse monate, guys. Can you see? Iphuma nje kamnandi nje. Just nice. So we can see that this is effectively 0,50 decimeter cubed. because remember the volume is in decimeter cubed, so remember that. Or if we wanted to convert it to centimeter cubed, so no one decided what is the unit, so normally we leave it at the decimeter cubed. So please don't forget this one. Ingasali mandingasali mandingasali dingenayuncedi. Can you see, guys? It's a killer one. It's a killer question, guys, but it's not a bad killer. It's a friendly killer because it always has some friendly reminders for you. So, okay, guys, you can plan this any other way you can see fit, but whatever you choose, make sure you stick to the plan and you try and be flexible around it and find ways of answering. As you could see, if you did not notice this portion of our statement, you are dead in this question because most likely you will end up there. But again, you're going to pick up some marks, isn't it? You will definitely pick up some marks. At most 3 marks up to that step. Right, you would get 3 marks. This is very important. Oh guys, andifuna nokuyimarka le iphambene, but masiyimarke ke ngoba ke seyiyamarkwa. Remember, in physics we get a mark for the formula, number 1. Number 2, we get a mark for the substitutions, isn't it? Number 3, we get a mark for that intermediate solution. Can you see those 3 marks are there because they speak to the table that we did. Nice. The next thing, this relationship is key, guys. That's the 4th mark. And that's the 5th mark. Right. And then, what are we doing? Substituting one into the other. That is more like simultaneous equations. We already have how many marks? 5 marks. So, literally, we can say this is the 6th mark and the 7th mark, provided you've got a unit. The mathematical gymnastics are not mark worthy. Literally, but it's more of those substitutions, those important points when you're using a rule like a law, substituting. That's like you created a law of simultaneous equations, and now when you substitute one into the other, it's more like applying an identity or a law of some sort. BODMAS, remember guys, 3-step approach. BODMAS, factorize, use a law or identity. This is how you score marks in the sciences, maths and physics. So it doesn't go away. So if you mastered this and you made it a ritual or a religion, you will never lose marks, even when you don't know the question, how to go about it. Some strategies can leave you somewhere with good marks, and then the rest goes to wherever it should go. Anyway, guys, enough of the rambles. This could be a very nice 17 marks, because if you really enjoy this section, you would know that this is fun. And I can tell you guys, if you really want to succeed in physics or maths papers, start with the difficult questions, because you want your brain engaged early. So start with the MCQs. While you're still on the momentum, you go to the hard questions. Again, you're going to skip questions. As you could see, some clues we got from the MCQ, some clues for the MCQ questions we got in the organic chemistry and wherever. So that is not a problem, because you start with the MCQs, you do your time there, because that is not something you can answer at a go and in a hurry. You can't. Then you come to these tough questions, because again, these ones need you to spend time. You need to spend quality time with them, because you need to understand everything you're doing, so that as you answer, you're getting your marks. And then, what happens next is the fact that once you take down these 2 big beasts, like question 7, question 6, and question 5, then you know you are home free, because electrochemistry and organic chemistry are easy. So you can take the easy one in organic chemistry, which is question 2. You chow that. It gives you some clues for the MCQs you couldn't answer. You go and sort them up, and vice versa. And then you go and take electrochemistry, because electrochemistry is fairly easy as well. Take maybe the electrolytic cell there. You chow it. Then you go back to question 3. It can be technical, because there's a lot of thinking and organization there. You chow that one. You go back to, say, the other question of electrochemistry, because it's also relatively easy. You chow that one. Then you go to the last big boy of organic chemistry, the organic reactions. And I can tell you guys, that way you will make sure you've answered most of the questions, even the tough ones as well included, and you will have marks. There's no way you can escape a distinction there. And that's all that matters. Leave the 100%ers to those who can get them. You don't need to worry about those things. Leave the awards to those who can get them. All you need is to make sure that your chosen career path is what you get to, because that is what is going to make your life easy or difficult. Anyway, folks, yandazi mos ngilapho uvulela kakhulu azalibali bakufanele aqhubeke nomsebenzi. Anyway, guys, I'm going to make sure that we cruise nicely on this question. So I think let's just get to it so that we can leave the electrochemistries. These ones can be easy to do. I'm just trying to bank some time because we had a break because of the noise with my student, and she might be calling me so that we can continue. So maybe let's just swallow this up quickly so that as soon as I finish with her, or I let her take a break, then we can finish the rest and then publish this for you guys. Of course, it's going to be late, but you will just do what you have to do. But those who are doing IEB, this will come in early and come in handy. Then you can get ready, because I can tell you with the confidence here for saying it, IEB is not different from DBE. In fact, IEB is easier than DBE. Look guys, the reality is, from teaching a lot of students, they all told me that the IEB papers, the higher order questions, they can approach better than the DBE higher order questions. So who's better then? Is IEB better in terms of it gives you the quality of your hard work? It gives it back nicely. DBE has a tendency to punish you, because it says even if you are prepared, sometimes it actually makes you feel like you wasted your time. But as a general rule, you cannot say something is completely weak and something is completely strong, right? Because again, the sections, sometimes they do more sections for IEB, more practical work as well. So sometimes it makes it, have the best experience for someone who needs more practicality to what they're doing. DBE, you will see that you will be preached to how to cram the exam guidelines and what. So it's more like theory. That's just where you can say, okay, maybe the divide here is the emphasis more on recall and abstract knowledge on DBE side. And then of course, if you come to applications, you need to have an in-depth knowledge. If you don't, then you fall off that wagon. But if you look at IEB, it just simply says if you attended class, you saw the experiments, you understand everything behind everything, you are most likely going to get the most marks, and you are likely to just score an easy distinction. Then for the best mark, of course, you need to be a little bit extra. You need to do more. That includes doing DBE papers. Nice and easy. Okay guys, let's go on to question 7. All right, folks, let's not waste time. It's not on my side. So question 7, the famous question 7. But there's really not much into this. It's always those higher order questions. Now, sulfuric acid is a strong acid. Yes, why? Because it ionizes completely in water or in solution. Now, it ionizes in 2 steps. Step 1 is hydrogen sulfate with water, and then it protolyzes water by giving it the proton, and then we end up with hydrogen sulfide. Hydrogen sulfate actually. This is sulfuric, it gives us hydrogen sulfate ion and the oxonium ion, and that is the acid right there, the strong acid. Then this is an ampholyte. It comes back here and acts as an acid by protolyzing water some more. And we call this protolysis, isn't it? Then we get the sulfate ion alone and the oxonium ion. Can you see we end up with 2 moles of oxonium ions? You guys call them hydronium ions, okay? It's one and the same thing. Those two words are interchangeable. Now explain what is meant by a strong acid. Can you see? Easy stuff. It already introduces itself, and then you have to then come up with a definition. So easy stuff. A strong acid ionizes, is an acid. Okay, let me just take this call. Okay guys, so that is it. We can say it's an acid that ionizes completely. In fact, the best word is to say almost, because it does not exactly do it completely, but that's the concept we preach here. It ionizes completely in water, right? And of course, some people can extend this explanation. This is enough to form a high concentration of the H plus ions. Okay, nice. So this is a more complete one, but hey, whatever you want to say it is important. So 2 marks. But even if you said it ionizes completely in water, that's fair enough. You get your 2 marks. Or you can extend this. This I would say it's optional, although it is quite key in a way. Anyway, 7.1.2. Now someone may want to argue and say, yeah, but what happens when this acid is dilute? And already it has a low concentration of itself. Therefore, how can it form a high concentration? Maybe we can say the highest possible then. Okay, again, let me take the call. Alright guys, so let's finish off this thing. Now it says here, give a reason why sulfuric is referred to as a diprotic. What does it do? It can donate times 2 protons. Okay, now don't write like that, write in words. Okay, now say we injury time guys, fever much, so we're just moving. 7.1.3 says write down the conjugate base for the hydronium ion or the oxonium ion. And what would that be? Remember, this is a strong acid. On the other end, it should be its conjugate, which is going to be a weak base, so it's going to be water. Now here they were just told us to write down, so we can write H2O however we want, or we write water, but we can't write both, or maybe we can write water in brackets H2O, or we can say H2O in brackets water. That is safer because you don't know sometimes how it's wanted, but when there's no specification, you can just do it however you feel like it. 7.1.4 says write down the formula. This time, can you see we need a formula of the substance that acts as an ampholyte during the ionization of sulfuric acid. Now which one? Now remember, the ionization is the forward reaction. Okay, now the forward reaction here, what do we see? Water is the base. Water is the base. So in this ionization, water is always a base. It's not an acid. So you can't choose water. But what acts as a base and a, and as an acid? Remember now, this is an acid. This becomes a conjugate base of our acid. Right? Right. Now this very same base is now an acid with its conjugate base like that. Can you see? So that becomes the ampholyte. And now the question was the formula. So this is HSO4 minus ion. Okay, that's the one. So don't find yourself saying something else. Okay, you will be dead. As much as we know water is an ampholyte, but we always focus on the forward reaction here, not the reverse reactions. Okay, forward reactions, maybe, not the reverse ones. And then, of course, understanding the acid, conjugate acid, don't. What did I write here? Yeah, irrite lento. Nice and easy, guys. Now, we are told here, 7.1.4 here, Now extra information says sulfuric acid has a concentration of 0.1 mole per decimeter cubed. And now here we need to calculate the pH value, and it's always something that we need. Now, to answer this 7.1.5, we need to know that H2SO4 in water will ionize, I don't know what that is, ionizes into 2 moles of hydrogen plus ions and the sulfate ion, isn't it? Because that's what this is. So now try and complex this so that we can perform the right calculations. So now we were given the concentration of 0.1. Now the concentration is going to be 2 times 0.1 for the acid, because the molar ratio is 1:2. Can you see? That works as well. So we go back and say, now you don't write this, of course. All you write here is to say pH is equal to minus the log of the concentration of the hydrogen plus ions. This implies that pH is going to be minus the log of, now here we're going to say 2 times the concentration of the acid. Somebody knows what you're doing there. Therefore, pH is going to be, and let's do it. So this is a simple calculation, minus log of 2 times 0.1. Easy stuff. So we are getting a pH to 2 decimal places of 0.70. Remember, the instruction said 2 decimal places. Now that is what happens there. Can you see? It's definitely an acidic pH for sure. Way less than 7. Nice and easy, guys. So obviously this is our thought process. Sometimes you can present this if you want. I mean, it shows how you determined your answer, but sometimes be very careful. But it doesn't affect our calculations anyway. So formula, general substitutions, specifically that calculation of the concentration, and the answer. pH does not have a unit, so we stop it there. Move along. 7.2. We are told to calculate, we are told 1.2 grams of anhydrous oxalic acid, that means this is powder form or solid form with no water, is then dissolved in water to make a 50 centimeter cubed solution. Now we're told to calculate the concentration of the oxalic acid solution. This is easy. Concentration is mass over molar mass times volume. This implies that concentration is going to be, mass is 1,2, divided by the molar mass of oxalic acid. Now we're going to say, now remember these subscripts matter. So we follow them subscripts. Okay? So this means we're going to have hydrogen is 1 times 2 plus carbon is 12 times 2 plus oxygen is going to be 16 times 4. Right? Right. And that's the molar mass. And then we multiply by the volume, but now the volume needs to be changed. So we can just easily quickly do it. 50 divided by 1000 is 0.05. Okay? So that is 0.05. We always change it to decimeter cubed when we do this. It has to be. Therefore, concentration of the oxalic acid, H2C2O4, is what we see there. So this is 1,2 divided by 1 times 2 plus 12 times 2 plus 16 times 4, close bracket. So you can just do it as you see it so that you cannot have to do too many things. And now we get what we want. So this is nothing but 0, now to 2 decimal places it's going to be 0.27 mole per decimeter cubed. The unit must be there when it is implied. So formula, this calculation per se is the most important in the final answer. The general substitutions are not so much. Yep. Yeah, but someone can add it if they want, but I mean, this is just too many marks already. And please don't do what I just did. Make sure you answer this properly. We must number things accordingly. If we don't do it, we are throwing away marks. Now let's get to the complexity of this question, which is this one. 7.2.2. So that we can end this pain. Now, I told you learners dissolve X grams of sodium hydroxide. Now that's already a question. To make a 2 decimeter cubed solution of sodium hydroxide. Now, I told you they transfer 25 centimeter cubed of the sodium hydroxide solution into a volumetric flask, and we can see it here. That's the one. And so this is that portion right there. And add distilled water. This is just meaning pure water without any other things to make a diluted solution. Remember, how do we dilute an acid? Do we pour acid? Okay, this is a base. It's not the story. It's not the story. But remember, you pour acid onto water when you dilute the acid. You don't pour water onto the acid. It becomes a nightmare. Okay, all right, okay. Now, this is a base. We can do whatever we want. Nice and easy. So can you see this is this distilled, or this is a lower concentration as a whole. Okay, great. This is what we do. So they're giving it to us nicely so that we can see this. But sometimes it's just these words alone. Of course, it can be left like that. You need to figure out this. And then we're told here, again, they titrate. These guys are doing a lot of things, eh? They titrate 43.8 centimeter cubed of the dilute sodium hydroxide. That means we just pour a portion of this against a 25 centimeter cubed of oxalic acid prepared in 7.2.1. So that means that concentration there is important. Okay, now the balanced equation is this. Good. Now we need to calculate the mass X of sodium hydroxide that was initially used in the 2 decimeter solution. So now where do we start, guys? We start here. We go back. So this is the plan. From here, what are we going to use? We've got the most information on the acid. We've got its volume. We've got its concentration. So this can help us to find out the concentration mainly. Okay? Because what is the use of this concentration? Remember, this is just a portion of the same concentration. So it will tell us the concentration of our base here. That concentration, when we find it, it's going to be the same concentration that we want here. So it's going to be X as well. But now once we have this concentration, then we tone it down by reversing the dilution back to what this one was. Because what this one is the same concentration as that one is. Let's say Y. So this concentration Y here is the same as your concentration of base is going to be Y, and it should be the same as the concentration of base in the 2 decimeter cubed. And now once we have volume, we've got concentration, we can work back the mass. Can you see? This is the pattern of thought you need to have in mind, because if you don't have this plan, then your calculations are misdirected and you are more likely not to reach the end. Anyway, perform those calculations because they will get you some marks. Now, let's go for it. We will start here. So we know one thing. We're interested in the concentration of the base. And remember, we were told the end point was reached. Did I read the whole thing? I didn't. To reach the end point. Now the end point, it means the titration is complete. And basically the definition of an end point, it says the indicator changes color. Indicator so it is the point in the titration when the indicator changes color for the final solution. So it means the titration is complete here. So if you hear that word titration or neutralization, that we will assume it's a complete unless someone tells us something is in excess. Okay, So this means we can plan this nicely and say, okay, since our target is the concentration of the base, we know that, well, the concentration of acid times the volume of acid is the same, over the concentration of the base times the volume of the base. It's going to be the number of moles of acid over the number of moles of base. This is only applicable when we reach the end point, meaning the total end of the titration, and nothing is in excess, but the solution at the end is of the resulting products of that reaction. Only then do you apply this formula. Please be very careful. When there's something in excess, you do not use this formula. Okay, please refrain. When there's something in excess, one of the reactants is in excess, meaning it remains after that, reaction. Just call it a reaction because we can't call it a titration right now. Now, this already means the word titration should already tell you that we must not have the acid remaining as well as the base remaining, but the resulting solution is of the products of that reaction. Whenever something is in excess do not touch this one. It's danger khefar. Right? Khefar do not try it. Now, we can use it now because we know that we reached an end point. So that means we ended our titration and the indicator changed for the final resulting solution, which has none of the reactants but the products. Nice and easy. Now, what are we going to say? This implies concentration of the acid is the one we calculated above. So this is 0.27 into the volume of the acid. Now, with this formula, we don't need to change those volumes. So what volume did we use? 25 over the concentration of base is what we want. What was the volume of base? Is 43.8 equals. Now, the molar ratio is from the equation. So this is 1:2. So this is 1 over 2. Nice and easy. So what do we do now? We do the cross multiplication and do the necessary gymnastics. So we can say therefore the concentration of base. So we can say the concentration of sodium hydroxide, the dilute. Remember, this is the dilute. Maybe let's put it nicely and say the base here is the dilute. So we can say the concentration of NOH is going to be 2 into 0.27 into 25 divided by this 43.8. Nice. Now can you see the centimeter cubed would cancel here? Nice. Let's get that concentration. So we've got 2 into 0.27 into 25 divided by 43.8 is equal to, okay, this is going to be 0.308. Now we want to protect our final answer, right? Mole per decimeter cubed. So this is this concentration right here now. It's no longer that value. That's what we targeted. That's what we wanted. So this is 0.308 mole per decimeter cubed. Oops. Okay, nice. Now, what are we going to do with that? Then, we know that essentially, to do the titration, remember now, if we have the concentration and volume, that means the number of moles in this of the sodium hydroxide did not change from the one that was that. So this then tells us that, okay, also, we know that C1V1 is equal to C2, Why? Because remember, the product of the concentration and volume is nothing but the number of moles. Same applies here. The product of concentration and volume, it's nothing but the number of moles. And why are these equal? Because in a dilution, the number of moles of the substance is the same, but the concentration changes. That's the idea behind this thing. So please know it, guys, so that you don't need a second invitation for this. Right? Right. Now the first concentration is what we want. So this is Ca into the volume is 25. Now the second one, the concentration is what we just found, 0.308. If it is wrong, you get a positive marking here. So this is 100, but I don't like that thing because it gives you the impression that you know the science, but you didn't go carefully enough to get it right. So that means the concentration of acid, of base, what did I say, acid? The concentration of base. So we can say therefore the concentration of NaOH initially is going to be this 0.308 into 100, oops, not 1,000, divided by 25. Nice and easy. So can you see there's a whole lot of steps to do here. So 0.308 into 100. We don't need to convert these when we have this situation. Then this is divided by 25. Now can you see the concentration is higher? We expected that. So this is 1,232 mole per decimeter cubed. Can you see this is this concentration right there? This is this concentration right here, the original. So this is going to be the concentration of base, which is going to be 1,232 mole per decimeter cubed. So can you see all of these steps are taking us backward? Now finally we are near what we want, the end. Then what do we know? We know that essentially concentration of sodium hydroxide is going to be the mass of sodium hydroxide divided by the molar mass of sodium hydroxide, NaOH, multiplied by the volume of the sodium hydroxide. But now volume can be water, we just leave it like that. Now we substitute. So what is the concentration? We got it, it's 1,232. Now this is what we want, divided by the molar mass here, sodium hydroxide. We know that this is 23 plus 16 plus 1 into the volume. It's already in decimeter cubed, so this is 2. So this is over 1. We do our famous gymnastic and we can make a conclusion that therefore the mass of sodium hydroxide that we used here, it's going to be 2 into 1,232. I'm feeling dizzy, guys. I'm hungry actually. Plus this 23. In fact, we can simplify that, but anyway, we can leave it as it is. Yo, guys, I feel like I'm going to faint. I'm hungry. Seriously hungry. 16 plus 1. Okay. Just a moment. I'm feeling heavily dizzy. Okay, this is divided by... actually, there's no need for any divisions. Okay, let's see. What do we get? This times 2 times this 23 plus 16 plus 1, which is 17. We just want to see what is cooking here. Well, what is cooking is this one. I'm getting 98.56 grams. Okay, that should be fine. It looks realistic. So this is it, guys. Can you see when you have the plan and the plan is, coherent, things are linked nicely, you just win. But of course, one can still approach it by making multiple steps of different number of moles and then making the relationships. But sometimes I like to use the means to an end, because what I'm interested in is what I want as the final answer. So I integrate my topics. Okay, so that's how I do it, guys, as you saw with most of my videos and most of my approaches. Okay, so guys, the formula that usually answers the question for me is the primary one. And these substitutions, whether this calculation or substitution, should be fine. And the answer, if it is correct, of course. Now that is 3 marks. And this is a mark 4. This is a mark 5. Ne? Now where's the other 2 marks going to come from? Now we can think about it. What do we do? So we have 1, 2, 3, 4, 5. Okay, guys, we can actually award this calculation, because that's a calculation on its own. So this is 1, 2, 3, 4, 5, 6. Now the 7th mark, guys, is your own guesswork, I suppose, in that at some point this substitution here for me is quite heavy, because to know that this is the concentration we need to put, I think it's fair enough. But anyway, by all means necessary, guys, get those 7 marks and walk away with those 20 plus or minus marks with a smile on your face, because you are doing well indeed. All right, guys, so we're going to carry on with these other ones and end this pain nicely. So I'm going to take a bit of you calculate the mass of the cathode after purification. Now there is that big one. We're going to deal with it when we get to it. Okay, so quickly, guys, let us do what is necessary. Now let me just eat something just to kill the dizziness, and then we carry on. All right, guys, let's get to the electrochemistry. Nice section as well. Okay, guys, let's do this thing and get it to stop. Sorry, a standard electrochemical cell. Once you hear that word standard, it means it's spontaneous. Okay, so it's a galvanic in a way. It's set up as shown, and we see there's a salt bridge, there's a voltmeter there, then we've got platinum because one of these ions is part of the the business that's cooking there. Then we've got lead here, the lead electrode with the lead solution. As you can see here, we don't have a solid, and therefore we needed this thing. Can you see we've been talking about these things all along? From the MCQs, can you see there was some sort of an ion that was not a solid in the reduction half reaction? Now we can see that we still have a similar situation where whether oxidation or reduction, but one of these ions is either acting as an oxidizing agent or as a reducing agent. But because it's an ion, we need a different electrode. Platinum is best because it can conduct electricity, meaning electrons, if this is an anode, can be stripped and transferred to the other side. This is the cathode. Electrons can be brought in through this so that it can affect the reaction on this half of the battery. Now we're told to state the energy conversion that takes place in this cell. Obviously, a galvanic cell generates electricity, so it's chemical energy converted to electrical energy. So this is 8.1. So we can say chemical energy is converted to electrical energy. Okay, great. This is very easy. 2 marks, nothing serious there. 8.2. Component Y ensures that the cell is complete. State 1 other function of component Y. It is to allow movement of ions into the solution. That is what it can do, because yes, it completes the circuit, but the main one, it allows electrical neutrality by allowing ions moving around. So we can say it, what can we say? It ensures yo guys, and as man, my writing now, I am not relaxed at all. My hand is just moving. It ensures it ensures electrical neutrality. Electrical neutrality of the solutions by allowing movement of ions into each solution. Okay, so guys, it completes the circuit, yes, but it ensures electrical neutrality by allowing movement of ions into each solution. So that is another business that it does. So whatever you said, you get 1 mark, okay? But I'm just trying to be as elaborate as possible, because guess what? Sometimes, it can hurt. Write down the reduction half reaction. Now, obviously, between lead and these ions, which one is the oxidizing agent? Which one is the reducing agent? Of course, we are looking for the oxidizing agent, because it is the one that gets reduced. Now we need to look at these ions in the standard electrode potentials. So we go back to that and say, okay, I like table 4a. You can use whatever table you are taught to use. For me, table A is user friendly because I don't get to go far. Now let's have a look. We know that the one on top on the left hand side is a stronger oxidizing agent. Now let's see. We saw lead ions, and there they are. There are the lead ions, okay? So there is the lead. Can you see? It's below the hydrogen standard electrode. So this is most likely a stronger reducing agent than an oxidizing agent. Most likely, remember that I said that. Most likely, I didn't say exactly. But now let's look at the ion 3 plus ions on the left hand side, because either ion 3 plus or 2 plus. But now what we see is 2 plus. Is this the one? But it goes to ion solid. So it can't be, because we saw ion 3 plus and 2 plus. Now there is ion 3 plus again, but where does it go to? Ion, so it's not the one. So this table can be quite challenging to use at times. And make sure, guys, you understand these things properly, because you will hurt yourself in the process of being complacent and careless. Now we can see that there's nothing more this side. That looks like what we saw. Then we come up and say, okay, there is ion 3 plus. Yes. What does it go to? Ion 2 plus. So that should be the one, because we saw 3 plus and 2 plus. Okay. So this means the oxidizing agent is the ion 3 plus being reduced to ion 2 plus. Okay. Even though in this setup they made it look like it's going the other way around, isn't it? Because they made it look like this is coming from here to there, but it's actually coming from here to there. So so this is what is important. So can you see, guys, using the standard reduction potentials properly, and also being careful, because there's a whole lot of possibilities. Make sure you choose the best possibility for the case at hand. Now we can just simply write this as it is. Ion 3 plus plus an electron gives us ion 2 plus. Ion is ion, all right? Right. So the reduction half reaction is going to be essentially ion 3 plus an electron going to ion 2 plus ions. So you don't need to write these ones, but you can write, because this is aqueous, meaning water-based solution. Can you see why did we choose this one? Because it appears higher than the hydrogen standard cell, and usually those are stronger oxidizing agents. On the left, of course, now we would see that the lead ions are a weaker oxidizing agent, and therefore they will not be the ones to prevail, but the ion 3 plus ions. And as a result, on the other end, the ion 2 plus ions are a weaker reducing agent, and that means this one becomes a stronger reducing agent. So this one becomes the anode in this cell, and it becomes the negative end or terminal of the battery. This one becomes now the cathode, and it becomes the positive end of the terminal. And in the cathode, reduction takes place. In anode, oxidation takes place. Good. And where reduction takes place, we call this one an oxidizing agent. And where oxidation takes place, we call this one a reducing agent. So these are just the things that one needs to run through in their mind as they continue to answer. So can you see, by just copying this thing in the standard reduction potentials, we get some fat 2 marks there. 8.4, we need to calculate the EMF of the cell. Now we go back and need those ones. We need those 2. Okay, so we know that basically the E cell is going to be E potential of the oxidizing agent minus the E cell potential of the reducing agent. Now this implies that the E cell is going to be, now the oxidizing agent is where reduction takes place, that is 0.77 minus, now this is where oxidation takes place, is minus 0.13. Okay, so make sure you copied those correctly. Therefore the E cell is going to be the addition of those 2. So what is that? So 0.77 is going to be plus 0.13. It becomes 0.9 volts. Remember, the final answer must carry the unit of measurement, volts. Okay, so that's good. Now, can you see this one gives you a bit of a back and forth into the information sheet. The best thing is to tear it off and keep it close to you so that you don't have to keep paging up and down. Now we get a mark here. By identifying those 2, we get 2 marks, and then the answer with the thing is very important. All right, 8.5. Now it says, how will the reading on the voltmeter be affected if? Now can you see, these are the interpretation questions. Now a deeper understanding of Le Chatelier's principle is very important, because these are by nature reversible reactions. Okay. Yes, and under standard conditions, we don't allow any influence by other things. So this is automatically a closed system. So think about it. This is nothing but chemical equilibrium and the principle of Le Chatelier coming for the second time. And of course, bearing in mind, these are ionic reactions in a way. So redox reactions and ionic reactions and acid-base reactions are just close associates. Now we need to be careful with ionic reactions. Certain things can cause precipitates to form and therefore nullify the entire process. So this is where that integration of inorganic chemistry, with other sections is very, very, very key. Okay, so we have point 8.5.1. Says the initial concentration of the lead ions is increased. So obviously, if we write the net ionic equation, because we would know this from knowing that. So the net ionic equation is going to be lead plus the ion 3 plus ions. Then we go on, we will have here lead 2 plus essentially what happens here is going to be ion 2 plus ions. Okay, so now we need to balance certain things now, because essentially this one only picked up 1 electron instead of 2, because this one can give 2. So if it picks up 1 electron, we need to double this thing, so it becomes 2 of it, so that it can take those 2 plus electrons. Ne? And then if this is 2, this must be 2 as well. That's it, it's balanced. We don't worry about the spectators at this moment, because they were not given to us. Now, can you see with Le Chatelier, we know that this is somewhat a reversible reaction, but we'll look at it in that manner. So what happens when we increase the concentration of these ones? Then more electrons are going to be given off. So we favor the forward reaction. And if we favor the forward reaction, we're saying we're transferring more moles of electrons. And if we're transferring more moles of electron, we get a current. The bigger the current, what happens? The bigger is the voltage, because according to Ohm's law, current is directly proportional to the voltage, provided we keep the resistance as a surrogate, of course, using temperature. See, all of these things in physics are coming back. So this should be increases. Okay, 8.5.2. Can you see there's a whole lot for you to justify this? You need to know these things. You need to know these things, guys. The molar ratios and what. Now, the surface area of the platinum electrode is increased. Remember, this one does not take part in the reaction, so it will have no effect. So we're saying remains the same. Okay, 8.5.3. Can you see all of that knowledge? This is chemically inert. It sounds like you're talking too much, but hey, you see now, this is coming to rescue you. Now the surface area of the platinum electrode, okay, so it says now the lead to lead half cell is replaced with the zinc. Now let's have a look. What happens? I mean, these are all of the same order, right? They release 2 electrons, essentially. So nothing is going to change here, honestly speaking, because lead and zinc can release 2 electrons together. Look at that. Look at that. So can you see, even though zinc is a stronger reducing agent, it just tells us the reaction is more likely to happen than with lead. But how many electrons does it give off? 2. That gives off 2. So if we're giving off 2 electrons, it's more like doing nothing here. So it should remain the same. Okay, it doesn't change. Yay! Wait. Okay, la. Let's be careful, guys. Remember, it depends on this one. Can you see? This one is much more negative than that one. Yeah? If this one is more negative, it means the plus sign becomes bigger, right? Right. So let's calculate this one. Actually, it just forces us to do this calculation for the second time. It's easy to make a meal, eh? Be very careful. So the standard reduction potential is what messes up everything, because if you look at it in terms of the electrons, you would lose the idea, as I just did. So what are we going to do here? We recalculate. It's going to be 0.77. But the ion one doesn't change. Minus into minus. This time it's going to be 0.76. Can you see? This one becomes bigger. It's 1.53. So it increases. So basically, this is also proving, because I mean, this is a stronger reducing agent, so it strongly does the job than that one would do. Should make sense, but yeah, sometimes the sense is from this particular calculation than the Le Chatelier's principle, because Le Chatelier will leave you hanging if you are just a chancer. So can you see, guys? Easy marks. So 8.6. Let's end this pain on this question. Explain the answer in question 8.5.3 by referring to the relative strength of the reducing agents. So of course this one is just saying we need to use the strength. So meaning the strength would also be something that has something to do with this. As you could see, we almost ignored it by looking at electrons, but its strength actually made more sense than the other thing. So we can say here, basically the zinc solid is a stronger reducing agent than the lead solid. Remember, this is the solid, okay? That's all. So reducing agents, it's either a solid or an ion or a gas, but that appears on the right. And of course, it's always the first one. So when we talk of reducing agents, these are the dudes we are talking about. The very first of each species on the right, on each table, A and what, those become the reducing agents, okay? Now, the oxidizing agents, again, is the first of the species that appears on the left of each. Those are oxidizing agents. The others are just there for electrical neutrality and balancing issues. So don't even look at them. So that's another thing you need to make sure is on point. Or the point is going to be made with you, if not with you, as an example. So again, guys, this is good. If we compare the two, we are good. Nice and easy. So can you see, guys, easy, 13 marks. Nothing really out of the ordinary here. Usually this portion can be easy, but sometimes it can be tough when you do the net ionic equation and balancing, when there's these permanganate ions and the dichromate ions. Now those ones will ask a bit from you as a student. Otherwise, this tola 14, says your balance is wrong. So if we 14 up, okay, let's end this pain, guys. Dikatele and hungry and have not rested at all weekend long. I just hope this video finds you guys in good time. Now, question 9 says, few drops of phenolphthalein. Sekuthethwa nge-acids and bases ngoba phenolphthalein ingenaphi apha. Iyaxelela le nto uba siya-integrate ngoku, siyaxuba, senza umxube vange ngoku. Ingxubakaxaka. I added 2 concentrated sodium chloride. Okay, but now what is the story? It's concentrate, this one. Okay, solution. Now the solution remains colorless. Uzama ukuthini ke ngoku? Uzama ukuthini, meaning the phenolphthalein is colorless. Now what do we know about phenolphthalein? When does it become colorless? Is it colorless in the acidic solution, or is it colorless in the basic solution, or is it colorless in the neutral solution? Now if you don't know these indicators, you are so screwed. If I was to use the wrong word, you will be dead in a minute. Okay, so phenolphthalein is a basic indicator, literally. It turns pink. Is it pink? Yeah, I think it's pink in a basic solution, but it's colorless in an acidic and neutral solutions. You understand? So if it is remaining colorless, it's either telling us we are neutral or we are basic. Or acidic. So now we cannot be sure where are we, because it's two things at a go, you see. Okay, guys, so technically this is something that suggests please check the indicators before you get into the exam room, because if you don't check, you can see, I don't remember so well, is it pink, is it orange? I think it's pink. Okay, but you have the luxury now of going back into the books and double checking. Okay, that is good. Now let's have a look. Carbon electrodes P and Q are connected. Can you see carbon, graphite? Why are we choosing graphite? Because the thing is, we've got ions here. You know, the chloride ions, the sodium ions, and the water molecule. It's a dipole, because remember this is aqueous, so that means we also have H2O here. H2O is partially positive and partially negative. It's a dipole. So be very careful. This one is also negative and positive like that. So this is cool. Now you can already tell this is more like a chlor-alkali reaction type of thing, you know. Be thinking of those things, and I've said these things a long time ago. So those of you who actually watched my 2005 video before the trial papers, yes, they got some benefit in this thing, but those who did not probably would be wondering why is cooking, what is cooking. Now it says, okay, connected to a battery dipped in the solution as below. Right. Now define electrolysis. Very easy. The process whereby electrical energy, because now we're taking electricity and we're driving a chemical reaction there. So the longer one is the positive, the shorter one is the negative. But now this Q becomes the cathode. Then that P becomes the anode. Now there's a switch in terms of positivity. The positive terminal is the anode, but oxidation takes place. Reduction takes place. Nothing changes in that signature. Okay, great. Now where cathode takes place, we talk of an oxidizing agent. Where reduction takes place, we talk about, where oxidation takes place, we talk about the reducing agent. Now, this is good. Now, what does this do? It makes this plate negatively charged. It makes that one positively charged. Easy stuff. Now, like charges repel each other, unlike charges attract each other, and those things, electrodontones, electrostatics. So this is 9,1. Now, electrolysis, we can just say a process whereby electrical energy is converted to chemical energy. Or someone can say it's a process whereby an electric current is used to drive a chemical reaction. There's many ways in which you can say these things. Of course, look at what is best and easy and safe. But if you're like me, you are someone who is not afraid to be adventurous with answers. You can do it. I promise you're not going to be victimized. Unless you're writing nonsense, of course. Now write down the name of the component that shows that the above cell is an electrolytic cell. Is the battery or power source. But this format is a battery. Ne? So don't write things that don't make sense here. It's literally, because we're told here, that shows that the above cell, can you see the above in this particular one? So it's the battery, this one. It's not any other power source. It's the battery. Or this one is a 2-cell battery. There's 2 cells. 1 unit, 1 unit. So those are 2 cells. Battery. So 1 mark. Can you see, guys? This is why you can come and relax here when you're getting punched by those big boys and girls. Write down the name or formula of the gas produced at electrode Q. Now, technically, essentially, zonke bonke. Now, this is where the problems begin, backwards. Because the technicality of this issue is that if you don't know this so well, you might as well go and study it. But there's no doubt about this one. It's the chloride ions that go there. Ne? This friend, let business can't that chloride ion is going to go and latch onto that positive electrode, right? Right. And when it latches onto that, what happens? The chloride ions become oxidized to chlorine gas. So here we will form Cl2, which is greenish yellowish. So there will be bubbles of chlorine gas here that are greenish and yellowish happening. That is the one. Now we will talk about why. Now the water molecule would not do it. Why? Let's go and look there. But there's some issues here that I have with this situation. But we will leave it at that because we know something about the water molecule. Now look, if we talk about this water molecule is a bit wrong. I don't know why. But because it comes to give us hydrogen peroxide, and this is not what we want. In fact, this is not what happens to the normal pure water. So maybe we can say this is not exactly pure water, you see. because we said the first of each are the ones. But the next in line is this guy, the chloride ions. Can you see? The chloride ions will oxidize to chlorine gas. And the next water molecule is the correct one here. This is the correct one. But this one gets oxidized to oxygen and hydrogen. And this is what we understand is going to be the case. But again, we need to be careful that there's also this water molecule down here. Now this water molecule down here, is it the correct one also? It is the correct one. But this one gets reduced to hydrogen gas and the hydroxide ion. And in the chloralkali industry, this is what we are aiming for. So technically, essentially, zonke bonke, this is the reaction we expect here. Because this is what would take place in the cathode. Remember, these reactions are inverted in a way. What was supposed to be undergoing, oxidation is now undergoing reduction, because in the electrolysis type of reactions, everything is inverted. But the competition still goes according to the strengths, isn't it? Yeah. It still goes according to the strengths. Can you see here the water molecule is a weaker oxidizing agent in this case. And if we follow up on this side, we don't see any other water molecule. Can you see? There's no other water molecule here. So we can't talk about that one, because this one is on the, in fact, I was making a meal of a situation here. Sometimes I don't know. Now I was looking at, remember there's a reduction taking place there. So now there's no reduction on this end with the water molecule. So I was actually wrong. You see? Now I'm hoping that you are getting the idea. Because remember here, there's a reduction. Right? There's a reduction taking place here. Now who attaches here as a result? Water can attach here because it's a dipole, meaning the positive end of the water molecule can actually come in here and do the things. But the sodium also can come in here and do the things. But now, which one is a stronger oxidizing agent between the water molecule and the sodium 1+ ion? Then we come here. I actually almost confused you. This is the one. Now look at the water molecule is higher than the sodium ion. Can you see? Now that is a stronger oxidizing agent than this. So this is why the water molecule is the one that actually latches onto our cathode and ends up undergoing the thing. So this is the guy that wins. Can you see? Even though this is inverted, we still use the same strength. So I was using the wrong comparison. A reducing agent against an oxidizing agent. This is where the big problems can come. I think in my previous video I made that meal. But anyway, I don't think I made that meal. Here I think it's quite easy to see who's going to go there. So the sodium cannot go in there because there's water that goes there. So if water goes in here, we're going to form the hydroxide ion and the hydrogen gas. Because we saw that when we do these things here, oops, sorry guys. When we do these things here, lama same thing, we get what? Hydrogen gas and the hydroxide ion or hydroxyl ion. Now, we can see that the hydrogen gas, the bubbles are going to form here. We are reducing the water molecule because it's a stronger oxidizing agent than the sodium plus ion on the standard electrode potential. So can you see, even though this is 1 mark, guys, this is not the question that, yay. Of course, if you cram and you have seen and you could remember these, but sometimes be very careful. Because there is a question that is very nice here. The question said this thing is concentrated. If this thing is concentrated, what on earth is going to happen there? Now that's a very big story. The sodium plus ions, it doesn't matter even if we make them many. They're not going to do a damn thing. They're weak, okay? They're weak. They don't change their strength because they're many. Although they can be here, but the one that is going to have to go out first is the water molecules. Then these ones can fall, okay? So sometimes this question can be technical. Sometimes it also makes me feel like I'm not sure what I'm saying. Anyway, somebody who knows this subject better, because I'm just a fanatic. I don't know all the full details. the compromises where they are and where they are not. So I just do what I can. Anyway, guys, let's move on. So it says write down the name of formula. So this is hydrogen gas. So you can write H2. So you write this one only, or you write the word hydrogen gas. So don't write both, okay? Only one or the other. But if you write both, you lose the mark. Nice and easy. 9.4. Now we are told to write down the half reaction that occurs at electrode P. Obviously, it's going to be the chlorine or chlorine gas. So this is 2Cl minus plus, no, we write it like this, single arrow, it's going to be Cl2 plus 2 electrons, because that is the oxidation reaction. Now let's go back to that one. Now this is where the controversies come actually, because we look at this one. Now in terms of reducing agents, now we've got a situation where we have this water. So this is the correct one. It's a reducing agent, right? Right. But we look at the chloride ions. They are a weaker reducing agent. Now, guys. Now we see that this is a stronger reducing agent than that. But again, if we look at, what we are trying to achieve here, this one doesn't achieve us what we want, because it says we just produce oxygen gas and hydrogen plus ions. And this already says this is acidified. Can you see? Now this is acidified. Once you see plus H plus, it means it's acidified. But now if it is acidified, what do we expect? Phenolphthalein to be colorless. Because even if it's neutral, even if it's acidic, phenolphthalein is colorless. Now this is suggesting that you could be playing the things there. Now this is when it gets complicated, okay? Because now the phenolphthalein, if they told us that it is another color, maybe we could tell what is cooking. But now, it leaves us hanging. So why do we not choose that water molecule? Why do we choose this one instead? Or why can't the water molecule be undergoing oxidation? Because it can. As we saw that this can go on and do that. But now this is a weaker, by the way, this is a stronger reducing agent. Stronger reducing agent than that one. But now why is the chlorine doing the things instead of the other one? Now I guess, guys, if water has already been occupied, I think the explanation I can give, which would make sense, is that since water is so obsessed with this electrode and doing its own thing, it doesn't have time to come here as well. It can only go in one side. Maybe we can say that's the rule. Except for our batanda yonke into badly salad, badly nyama, badly papa, a bit of everything, then there's a problem there. But tatile. If this one is going this way, we can say maybe that one is going that way. Now maybe this is when this portion of saying concentrated also comes in. If we took water molecules into that, there's not enough for them to compete against the chloride ion, you see, because we already eliminated some here. So that means the concentration of the water molecules will drop, and therefore it's not enough to come and do things here. So the chloride ions have a better chance here than they would elsewhere. So this is what would make sense. Now you see the concentrated actually explains that part. So be very careful. It explains that part in that essentially, although this is a weaker reducing agent compared to the water molecule, but because we're already eliminating some, so there's no chance for them to also come here in equal numbers to do the job. But the chloride ions are many, so they will do the thing. They will be the predominant gas that forms there. Okay, so I suppose this settles the debate, and you can easily understand now the dynamics of the science itself, why certain things go on in a certain way. And in fact, you can see it practically. It does happen like that. So it's not even to say it's just a matter of an abstract thought. No, it's actually one that was fueled by experiments. And then understanding how reaction rates are affected by certain things and products and what. Then we can easily say, okay, all right, okay. The collision theory says the one that has a higher concentration has a better chance to collide effectively where it's supposed to collide, isn't it? Great stuff. So I'm sure we now are happy that, okay, this should be indeed the one because of too many of those ions compared to the water molecules, which we already taken out in the first place. Now let's go on 9.5. Now it says, and be careful, single arrow, guys, it's important. And we write the reaction as an oxidation half reaction technically. On the table, it's moving from left to right, but on the book, we write it accordingly. Okay, great. Now, phenolphthalein is colorless in acidic solutions and pink. Bayasinikeza nina nidinga sininqabuze apho ilanga lingashayini khona. Yes, is an alkaline solution. Okay, in an alkaline solution, it's pink and it's colorless in an acidic solution. So now this one is helpful because we could have forgotten this one. Now it says write down the color of the solution around electrode Q and the formula of the substance responsible for the color. Now, do you see where this comes in? Think about it. What did we liberate around electrode P? As we formed hydrogen gas, we were liberating the hydroxide ion. This is a strong base. So it means this is going to be pH. So that means the pH around this electrode is going to be greater than 7. And therefore we'll see a pink tinge here. I like this question, man. It's beautiful. This question is super duper beautiful. Now it starts to make it more fun to do science than the misery of just cramming. Mega was the king of what? 19 so and so, this nonsense happened. Like it's gone, guys. It's not coming back. Why the heck are we obsessed with what is not doing anything anymore? Okay, we get old. You need to know your past so that you can know your future and understand your present. Oh, okay. All right. Okay, we get it. Now we accept it. Now, can you see, guys, it says write down the color of the solution. It's pink. And the formula of the substance responsible, it's nothing but, maybe when we say substance, is basically the OH minus ion, right? Because that's a strong base. But someone may want to write the entire substance. It's going to be sodium hydroxide because that is a substance, but this is an ion. But an ion is an ion of a substance. So, hey, I don't know. Inkinga seyifuna uba khona ke manje na uzobe sozibonela ukuthi wenze njani. Ngelinye ixesha uthi soyifumene impendulo ubethwe into ba do I write sodium hydroxide or do I write the hydroxide ion? Bafethu inkinga ikhona. But into esiyaziyo ukuba the highest concentration of sodium is going to ensure that these ones collide faster and furiously so. Then they will form the sodium hydroxide. So I do believe, yes, as much as this is the one responsible, but if someone writes sodium hydroxide, they should be forgiven. This is where we cannot argue about the forgiveness, you see. Yeah, we can't. And this one we can also accept. In fact, that is the main guy, but we can accept that substance over there. So 9.6. Now here is a bit of a situation right here. An electrolytic cell is set up for the purification of copper, or that contains zinc and platinum impurities. Now platinum is non-reactive, so we don't worry about it. It's not an issue. But the cause for concern here is this dude, because this one is highly reactive. It's going to cause issues. Now after the purification of the impure copper was completed, now we see 1,38 times 10 to the exponent minus 2 mole of electrons was transferred. So this one has made this question a bit easier because technically, once we know the number of moles of electrons, so we can easily determine the mass. We don't have to worry about Avogadro's Avogadro's constant coming together with the Faraday. In fact, determining the Faraday's constant, when we take the Avogadro and multiply by the charge on an electron or elementary charge to get that constant, and then we do all those gymnastics. Sometimes this question can be complicated, okay? Yeah, but this one is making life easy, because once you know the number of moles of electrons, then we are home free. Now it says now the initial mass of the cathode was 2 grams. Nice and easy. Now it says which metal besides copper will be oxidized. Which metal besides copper will be oxidized? Is it zinc or platinum? Obviously zinc. Why? It's more reactive. Platinum is inert. It's chemically inert, this one. So this dude is not going to cause us any problems. So when we're made to choose, we choose zinc. This one is chemically inert. I see P in the Lord. The one back dollar C talento. Now it becomes an advantage. Here, it sounded like we're crazy singing about it all along from MCQs and war. But now we know. We know that this thing is chemically inert, so it's not gonna react. Right, even if you check here, what I think ikhona equal. Nansi apha phezulu. Yo, ikhona le platinum phayana. Kodwa ke ngoku uyabona platinum, it's a weaker reducing agent. So it would not, essentially. But zinc is a stronger reducing agent. It will definitely be oxidized. Ne? Okay. All right, okay. Sorry, guys. This is very important. We do what we have to do. Okay. So this one is going to be 9.6.1 is going to be the Zn. Or maybe let's write according to what our choice. See, don't write things that you think of. Remember, we're given a choice. Zinc is written in full. Ungazobhala Zn ke apha. Siyayazi bavele. Uyakwazi ukubhala kanjalo kodwa ke ngikubhale lento ixelelweyo, ungabhali lento icingayo. There are certain questions that demand your attention, even though you could attend to it differently. But this one says, ndifuna unjonge straight emehlweni. Ungaphanyazi nokuphanyaza, because waphanyaza ndikufaka inqindi. It now says calculate the mass of cathode after purification. Now the cathode was already 1 gram there. Now we are going to add some more. But now the nice thing is we know that with the copper, this is the one, Cu2 plus 2 electrons, it goes to copper solid. You see, so there's 2 moles of electrons that we are seeing here. Now we can see that technically, if 2 moles is to 1, that means we will have to halve these electrons when we get to here. If we want the number of moles here, technically we are going to take it to half of this one. Then from that half, what are we going to do? Yes, 2 moles is to 1, so it's gonna halve. So from this equation, you can even write this one and say Cu2 plus, maybe let's write it like so. From, sometimes be creative, guys. Please, we can't respect people who are stiff here. We respect people who are creative in nature, because that's the essence of learning. We learn so we can acquire and amass skills, which we will display with creations and innovations, to then show the significance of doing all of this learning in the first place. Now we can see here 2 mole of electrons produce 1 mole of copper solid. This is key. Don't shy away from stating this thing. We can even write here produces or yields 1 mole of copper solid. This implies, because this is what we're trying to do, this implies that the number of moles of copper that we produced is going to be equal to half the number of moles of electrons. This is the essence of all of this thing. The number of moles of copper is going to be half of this number of moles. Now this is 1,38 times 10 to the minus 2. Therefore, the number of moles of copper formed, isn't it? Yes. Maybe we can even write it. The number of moles of copper formed, because we want to show that this is the case. Format is this one. So masikhawuleze the same guys, 0.5 into 1.38. Yo, afethu kuthi ndihambe straight ndiyolala ngoku ndidizi la way yasemdantsane kwabo basuke eMonti. So 6.9 times 10 to the minus 3, sorry. Now this is mole or moles. All right. Now what are we going to do? The question was not about the number of moles. It was about the mass. Then we know that the mass of cathode. Now we want to be very good at this thing. Okay, man can balance into calculate just for the vibes. Mass of cathode is going to be 2 grams, the initial one, plus the mass of copper formed. Okay, so this is going to be 2 plus the mass is going to be number of moles times. Now guys, balana new formulas. Times 10 to the minus 3. Send your 9 and none is those baleli formula. We multiply by the molar mass of copper. Molar mass of copper. First copper, there is the copper, there is 63.5. Okay, senvele ndajaha ke bafethu nani yazibonela ukuthi sekumoshakele ngo. And therefore we can say therefore the mass of cathode is going to be that situation going on in there. So we multiply that answer we got by 63.5, we get that 1. It gives us a very small mass indeed. So this is 2 plus 0.4, let's say 38. Now we add 2 to that. So this becomes now 2, this is 4 grams now to 2 decimal places. We can leave it at 3 decimal places, it's okay. So that would be the mass of the cathode, after the purification there. Remember to tell us the unit of measurement at the end of your gymnastics. Now folks, it helps to understand the equations that govern certain calculations stoichiometrically. This is theoretical things, it's not the actual thing. If we want the actual thing, we can measure this by actually measuring this thing nicely. So the actual way of doing it is to take the cathode again, and we measure it at the end of the purification, and when the things are tinging there, then we can tell how much mass we actually put on. But theoretically this is the one. And now when we are asked to find the percentage purity of the copper in the cathode, then we are going to say the percentage purity is the one that we actually added, because we'll measure the cathode before and then the cathode after. The difference is going to be the mass of copper that we attached in there. And then that mass of the copper that we attached in there is actually this number of moles that we calculated here. And then now we take those ones and then we're going to divide by the actual ones that we find from calculating the actual mass. Then we multiply that thing by 100%. And guess what? That thing gives us the percentage purity, because that question can be asked here. Don't think because it's in grade 11 it's not going to come. It's going to find you. Even in electrochemistry, it can be even made into a 10-mark question and complicate this thing and not tell you the number of moles. And now you start crying and you're like, yo, kwenzeke ntoni phayana, kwenzeke umhlola. Okay, now folks, this thing is long, guys. I don't know how long you're gonna have the attention here, But I do believe those who are lucky to see this video while it still is within time for them to see it, I think you will have learned something, but it's more appropriate for those who are going to upgrade next year, to be honest, because this gives you enough time to appreciate the science, to appreciate the techniques, the tools, the knowledge, how you apply it, and how you use everything in front of you. But for you who are already writing, if you have not been a follower of my channel, you may actually find it a bit more strange to follow on these videos, because I'd probably be introducing something you're not used to. But for those who have been, fanatics alongside me, then they know that they have been seeing this thing and they've been trying it out and they've seen whether it works or not. And now this doesn't come as a surprise. But it doesn't mean you wouldn't learn. Like I said, if you're new to this channel, rather pause every question I go to, try it first, and then get stuck, look at the video when I explain, and that way you can get maximum benefit in the shortest space of time. If of course you don't have anything else that you can do. And like I said, I highlighted certain areas to go and look at. Definitions, for example. Look at things like the table of indicators to know their pH ranges and their color changes, because that can be important in acids and bases. As you could see, it applied even in a topic you didn't expect it to. And then so things like that are very important. Also brush on the calculation, stoichiometry. How do you relate things to each other? What exactly? It's actually the changes that can cross the equation lines, right? Otherwise, the other things that are not the changes, they do not cross the equation line. So be very careful. Then organic chemistry, guys, master the organic reactions, reaction conditions. These are the things you would want to look at extra after watching this video. If this is the only thing you could do for yourself to revise, and I can assure you, you would get a decent mark. 60 plus is yours, even if you didn't practice other question papers right now. Provided you're going to go and get a good sleep after this thing, and do your part of, cross-checking, double-checking, revising here and there, putting it together, trying some other questions in the similar framework so that you can be in a good shape. Otherwise, guys, let me not prolong this. It's already too boring and too long and too late even, but I apologize, guys. I actually hoped I would deliver this video yesterday already, but the commitments unfortunately took me to the ends of the world. Even now, I have not really rested well, technically. This is now for 3 days in a way. If only you knew, guys, the amount of work that goes behind the scenes in doing these videos, you would laugh how long it takes to actually do this thing, to go through the process. I even torture myself by doing this live, as in already recording and doing everything from the start to finish, not necessarily preparing one portion and then try to do a quick video and then edit, and then I give you a short version of it that is on point. Because the idea for me of not editing these videos, although I could, is just to show you guys how long it takes you actually to work through your craft. It doesn't just come with magics. So editing for me is not, in fact, I'm not even able to do it. Maybe let's start there. I can't even edit. So again, maybe it's my weakness than my intention, but I think it's my intention than my weakness, because I can learn how to do that thing in just one day and then I can do it better. I'm creative, by the way, in nature. I'm very creative. It's just that I have decided to just, null certain parts of my abilities because they are no longer relevant. But when the need arises, I can rise up like a beast. But yeah, that's the idea, guys. I'm just not editing these videos deliberately. I know they're long and boring, but if you're a student who really gets bored by that, it already says you don't have the appetite for learning. You should already just stop learning. Might as well go and do creative arts and stuff. Join politics. But if you really say you want to learn, you want to go to university, this is already a preparation for university, because guess what? Most of the work, hard as it is, it's going to be you doing it. The lecturers are going to be like going through like these short videos on YouTube that you guys watch so much. They would be going through, you're like, yeah, it sounds right and cool, but I don't understand. And now they don't have time to explain it to you nicely and in a long way. So you'll find that if you're already not in this mood of doing things, you're already going to doom yourself in university, because you'll be one of those who go in there and fail miserably, because there's a lot of work there to be done, but no one is going to show you. So you might as well learn how to do things properly from the ground up. And these videos are trying to inspire that, because I know these are some of the challenges my colleagues at varsity, even I myself, have had a few challenges. But the one thing that gave me an advantage was because I was already doing things this way myself on my own, even at matric. In fact, I tended to become more of a teacher to my colleagues than actually benefiting from them. Of course, I benefited indirectly, because by teaching them, my understanding became more enhanced. So it was easy for me to pass, even if I bunked some classes and lessons. I knew how to get it going. But some of them would not survive if they didn't go to class, they didn't have the scope, they didn't see the past exam question papers. I hardly did those things at varsity. I'll just read my textbook, take my notes, take my course guideline, and see what are the targets, and try to study alongside those targets and challenge myself with the questions, because I knew I'm preparing myself for a greater future where the disease is not going to tell me, hey, I'm TB, I'm not pneumonia from Staphylococcus aureus. You see, and this Staphylococcus aureus is the MRSA. Okay, the multi-drug resistant one. It's not going to tell me and warn me. I have to be quick to notice, quick to tell the difference, and quick to even make the diagnosis, so that the action plan is timed, so that we don't lose an individual. There's no past exam question papers for the diseases you're going to have to treat. And that's why mismanagement of patients occurs, because of people who are taking purely survival techniques from matric and carry them through university and expect to become the excellent professionals. It's not going to happen, guys. You have to do the right thing, and it hurts to do the right thing. And sometimes it benefits you less in the beginning, but in the long run, I assure you, they will all think you are the most blessed, because they don't understand where you've been. They don't understand what it takes to get there. They think it's just a plug and go. It doesn't work like that, okay? Anyway, guys, enough of the nonsense. Before I take forever, I would say to you guys, good luck with your exam tomorrow, and good luck with your futures as well, because this is the end of the road between you and I, class of 2024. But it may be a continuation of the road. I'm saying maybe. It may be a continuation of the road in the following year. But again, my channel has everything that I think I had to offer. I don't think there's more. I'm almost reaching my ceiling when it comes to what I can offer, because now what it's going to end up looking like is just me showcasing my knowledge and my abilities, but it's not really going to be any different. So this means you probably are better off now with all the videos I have in the channel. If I add more, it would be probably that question someone is struggling with, and I felt it has some secrets to share. It could be that question, that I felt was giving a lot of people an issue, and I think I have something to tell. But I don't think it would be prudent for me to just go through all the past exam question papers in the same way, one after the other, because it will give you the false impression that you are learning when you're actually not. When I'm doing it, it's easier, because my thinking is already at that level, but is yours at that same level? That's the question. That's why you need to put it to the test first, and the strenuous exercise, and you will feel like it's not doing it. But you keep going until it clicks, because it will eventually. All right, guys, goodbye. Good luck for tomorrow. And thank you very much for supporting my channel, guys. I appreciate your comments. I appreciate your sharing my channel with your peers, and you've been doing it consistently. Every week I get reviews that you have shared, and very greatly so. So I appreciate that, folks. I never thought at this stage in my life I will have done such a stride on YouTube doing educational content, because trust me, it's not easy to sell what is important and useful and meaningful. But it's easy to sell rubbish, because if you start controversial topics, talking nonsense, stealing people's work and making it yours so that you can also shine, it's easy there. And you become popular, you amass subscribers to just show your multitudes fans of nonsense. Unfortunately, that's just how it is. But good stuff, no one likes it because it's a lot of work, guys. It's a painful exercise, but very meaningful at the end. Hey, I'm starting the nonsense again. Goodbye and good luck. I love you all, folks. And it's all for the love that I'm doing all of these things and torturing myself. And I hope you benefit and benefit greatly. Make yourselves proud and your families and those around you. Until we meet again, goodbye.